Europa is universally recognized as a prime candidate for locating extraterrestrial life within the solar system. This is due to the abundance of water, likely in a liquid state, safeguarded from the extremities of space by a substantial covering of ice. The ice displays agitation, perpetually fracturing and moving in rafts and slabs, reflecting the gravitational influences of Europa's substantial parent planet, Jupiter, and its larger neighboring moons, Io, Ganymede, and Callisto. Gravitational flexing is merely the beginning of the narrative. A fragile atmosphere is being disrupted by Jupiter's intense radiation, which disassociates water molecules at the surface into hydrogen and oxygen atoms. A little distortion of Jupiter's electromagnetic field at Europa indicates the presence of a metallic core, a saline ocean beneath the ice, or both, which rotate asynchronously relative to the planetoid's surface. This may indicate either an internal heating source from radioactive decay in the core, robust global water currents, or a combination of both. Europa's deep ocean may contain thermal vents, hydrogen sulfide emissions, and organic compounds, such as methane originating from the mantle. These may offer additional energy alternatives and serve as the foundational elements for polymeric chemistry, facilitating life's prerequisites. Galileo initially observed Jupiter's moon, subsequently dubbed Europa by Simon Marius. It appeared as a mere second dot in the sky, adjacent to its home planet. Only after the transmission of close-up photographs of Europa from the Voyager 2 flyby in July 1979, did the distinctly unique characteristics of Europa become apparent. A satellite, marginally smaller than Earth's moon, exhibited a markedly distinct characteristic. The solar system's smoothest and most luminous surface, nearly devoid of craters, yet interlaced with elongated lines and arcs reminiscent of a fractured eggshell. We understand the likely composition of the interior of this globe. Given our accurate knowledge of its volume and the method to compute its mass based on the gravitational attraction that alters the trajectory of passing spacecraft, we can ascertain its overall density. Given our knowledge of water's density, we can ascertain that water ice alone cannot constitute its total mass, indicating the presence of a solid mineral core. Determining the internal dimensions by conceptualizing a stony silicate mantle surrounding an iron-nickel core, and understanding the densities of silicates and metals such as iron and nickel, provides a reliable estimation of the internal size. The biographic signature, smooth surface, and elevated albedo indicate that the surface is solid ice. The surface is firm yet dynamic as the always shifting ice plates glide, collide, and reorganize in a tumultuous arrangement. Extensive fissures across the planet, exposing surface fractures and potential subterranean explosions. These lines are not consistently linear. They resemble soft arcs and frequently intersect at right angles. Significant slip faulting occurs when frozen surface plates glide past one another, resulting in intricate geometric formations. These formations are occasionally filled with ascending liquid that freezes into deeper holes over time. In the chaos zones, ice plates drift over one another, resembling disordered jigsaw puzzle pieces. In contrast to those on adjacent Ganymede and Callisto, the significantly reduced quantity of craters indicates a surface that has been repeatedly, or at least recently, resurfaced. All the aforementioned qualities align precisely with the predictions for a frozen water shell subjected to tensile and compressive forces due to the intense gravitational influences from within Jupiter, Io, and the orbit of Europa. The possibility for ongoing compression and expansion to generate heat increases the probability of ice melting beneath the surface. A significant indicator of a subsurface liquid ocean is the presence of anomalies in Europa's powerful electromagnetic field caused by Jupiter. The simplest explanation for this phenomenon is a mobile, electroconductive substance within Europa, such as a dynamic, saline liquid ocean. Indirect evidence indicating that internal rotation exceeds surface rotation bolsters this viewpoint. The final observation regarding the surface is that the fragmented ice fragments adrift and the extensive fracture lines, bordered by minerals, suggest the presence of a layer of dynamic saline water beneath, which facilitates the movement of the ice plates above. A distinctive characteristic shared by only a limited number of celestial entities in the solar system is the existence of an oxygen-rich atmosphere. Europa's atmosphere is exceedingly tenuous, comprising merely 1/100th of Earth's air and considerably less dense than Mars's. Due to minimal atmospheric filtration, radiation dissociates water at the ice surface into hydrogen, which easily escapes, and oxygen. By gardening the recently liberated oxygen into the ice and maybe integrating it into sporadic liquid eruptions above the surface, oxygen may gradually infiltrate subterranean interactions with other molecules prone to oxidation. The atmosphere of Europa is exceedingly sparse, offering negligible protection against radiation or meteorites. Radiation continuously generates oxygen, whereas most released hydrogen rapidly dissipates into space. Despite the absence of meteorite protection on the surface, the lack of craters suggests a continual transformation of the area. The origins of Jupiter's 4 principal moons are analogous. However, they exhibit considerable variation in size and spatial arrangement. Before examining Europa and Io in the subsequent chapter, we will elucidate how they attained their present state. 1. When created from a substantial cloud of gas and dust, approximately 4.5 billion years ago, 99.8% of the mass accumulated in the Sun at the core of the rotating protostellar disk. The remaining 0.2% consisted of all the planets and their satellites orbiting the Sun. 2. A portion of the residual material was integrated into the construction of Jupiter and its moons, rendering it the most massive planetary system orbiting the Sun. 3. Of the total, 99.98% entered Jupiter, while the remaining fraction was predominantly allocated among the 4 principal moons: Io, Europa, Ganymede, and Callisto. 4. The phase entailed the synthesis of metallic and silicate compounds in the presence of water and volatile gases. The metals and silicates constituted solid cores. These identical factors likely expelled whatever water was initially condensed there. Europe. Europa's proximity to Jupiter enabled it to maintain sufficient water to envelop its whole surface, while its remoteness from the Sun resulted in a total surface freeze. Tidal flexing and potentially radioactive heat generate the subsurface liquid. It continually ascends to the surface, complicating the assessment of the extent of a meteorite strike it receives. Ganymede, situated on Jupiter, is the biggest satellite in the solar system. Ganymede's water content is proportionally akin to that of Europa. Nevertheless, despite its internal heat production, Europa's surface exhibits markedly lower temperatures, resulting in its eventual resurfacing. Callisto, a moon of Jupiter, is the 3rd largest satellite in the solar system. Its internally produced heat is much less than Ganymede's, leading to a geologically dormant and old surface. Due to a resonance period of 1 orbit around Jupiter for every 2 orbits by Io and 2 orbits around Europa for each Ganymede, Io, Ganymede, and Europa would oscillate in proximity. This guaranteed that Europa would undergo adequate tidal flexing to inhibit heat from penetrating its interior. Combined with some radiogenic disintegration, particularly in its early history, this has produced a liquid ocean beneath its frozen surface. Examining the essential ingredients for life indicates that Europa is an optimal location for solar system visitors seeking extraterrestrial life. Initially, Europa possesses a greater volume of water than Earth. And considering the numerous beneficial properties of water as a solvent for biological systems, the requirement for a solvent is inherently fulfilled. As evidence increasingly supports liquid water beneath the frozen crust, multiple potential habitats for life have emerged. The mantle at the bottom and the boundary at the top coinciding with life on Earth. If water serves as the solvent, carbon is the most probable backbone for the polymeric chemistry essential for life. Direct proof of organic molecules on Europa is unavailable. If the satellite's interior resembles Earth's organic chemistry precursors, such as methane, carbon dioxide, and hydrogen sulfide, may be released from Europa's subaqueous rocky mantle. We have delineated the benefits of light as an energy source for biological systems. It sustains the predominant portion of life on Earth and invigorates any life that may exist in the clouds of Venus. Despite Jupiter's considerable distance, the light would possess around 1/20th of its intensity on Earth, potentially sustaining the surface-dwelling life of Europa. The severe radiation and extreme cold on Europa's surface probably restrict any life near the surface to microbes residing in hypersaline water inclusions deep within the ice. Sufficiently distant to receive some radiation shielding, yet close enough to absorb the scant millimeters, several inches, of weak sunlight that penetrate the ice. Photosynthetic microorganisms represent the initial form of life we find upon our arrival at Europa. Even from the remote sun, a powerful ionizing and particle radiation field strikes Europa unimpeded. These highly charged particles might impart a substantial energy dose to any surface or near-surface organism capable of harnessing it. The direct utilization of particle radiation as an energy source is impractical due to its intense and erratic characteristics. Collisions with radiant particles are more likely to produce hydrogen from water, potentially serving as a source of metabolic fuel. If water dissociates into hydrogen and oxygen within the ice, a reservoir of hydrogen accumulates, establishing a concentration gradient that promotes hydrogen migration into biological compartments. If organisms have developed the mechanisms to capture energy from the diffusion of hydrogen ions across their outer membranes, then usable energy could be extracted. These organisms would also be microbiological, as they would presumably be enveloped in minute water inclusions. Nonetheless, the oceanic depths beneath the ice invite life in more substantial forms and increased diversity. Even the most slender predictions for the ice sheet on Europa indicate that it must be a minimum of several kilometers thick. This renders the underlying liquid ocean entirely devoid of light, notwithstanding the potential presence of infrared radiation from certain thermal vents. If no light reaches this aquatic habitat, alternative energy sources must support the ecosystem's familiar forms of usable energy. Hydromethane, comprising carbon dioxide, methane, and blue chloromethane, is accessible as a net energy release. Due to unidentified chemical processes, hydrogen and carbon dioxide may emanate from the mantle's interior. As outlined in Chapter 3, iron is a substantial atom that readily acquires and relinquishes electrons. If iron in the ocean is reduced by hydrogen emanating from the interior, this process could also yield energy. The oxidation-reduction cycle must be fully executed for these reactions to function perpetually. The reduced ions must be reoxidized. Carbon dioxide and iron ions. This may occur at the ocean's surface due to oxygen permeating the ice cover or unexamined chemical reactions at the seabed. Organisms on Earth can execute the aforementioned reactions within their cells, using the generated energy as chemical bonds to fuel their biological functions. The convection of water currents beneath ice constitutes an additional potential energy. Although there are no known instances of animals on Earth utilizing kinetic energy to sustain fundamental metabolic functions, it is acknowledged that it contributes to specific biological processes. Certain coral-like, flat, fan-shaped animals adapt to current flow to capture microscopic food particles. Dynamic fluid waves deform the hair cells in vertebrates' inner ear, transforming sound's mechanical energy into neural impulses. Air currents facilitate avian flight, dissipate heat from animal bodies by evaporative cooling, and convey nutrients via the circulatory systems of both plants and animals. Cilia, influenced by water currents, may impart tensile energy to molecular structures akin to spring coiling. Upon the release of tension in the spring, energy for labor becomes accessible. Conversely, the bending of hair cells may activate semi-permeable pores, facilitating the movement of ions along their concentration gradients. Flowing ions may facilitate the storage of chemical energy for subsequent metabolic release. The imaginative character of evolution enables us to conceive numerous mechanisms. The potential energy derived from ionic concentration gradients is a viable source of biological activity in Europa's vast ocean. The salt concentration of water is greater near the ocean level due to the dissolution of minerals from the mantle compared to water at a higher elevation above the ocean floor. The melting ice at the ocean's surface, characterized by a notably lower salinity, makes the seawater near the surface more diluted than at further depths. Living organisms can harness energy from these gradients by sustaining an internal ionic concentration, or tonicity, that differs from their environment. Energy could be extracted from the ocean floor by permitting ions to pass from regions of higher exterior concentration into a live cell's more dilute, hypertonic interior. Alternatively, organisms near the ice ceiling could extract energy from ions that diffuse outward from their hypertonic interior into the hypertonic environment. These occurrences reflect the osmosis process akin to the movement of water. Water's spontaneous movement into or out of a cell at the ocean floor or the ice sheet's surface may be linked to mechanisms within the cell membrane that alter the structure of molecules responsible for chemical storage or initiate chemical reactions that conserve energy for future utilization. Heat does not serve as a source of metabolic energy for life on Earth, likely due to its rapid dissipation and comparative inefficiency relative to light. Nonetheless, it may provide a significant energy source in the perpetual darkness of Europa's subterranean ocean. Heat may originate from two sources: the radioactive decay of minerals in Europa's metallic core, which generates heat that influences tectonic activity on Earth, or the tidal forces exerted on Europa by Jupiter and Io in one direction, countered by the gravitational pull of Ganymede and Callisto in the opposite direction. Certain scientists propose that the diapers, or upwellings in the surface ice, regularly observed on Europa, are a consequence of the thermal ocean. The island sifting of ice islands and the extensive curvilinear fault lines on the surface indicate that forces capable of producing significant heat play a role in Europa's dynamic characteristics. Regardless of the heat source, once thermal gradients are formed, the transfer of heat along those gradients, or the containment of heat from them, could function as energy sources. Jupiter exerts a substantial magnetic field across its principal satellites, and the variable gravitational pull constitutes a genuine, albeit feeble, force. An organism that has developed the requisite transducing systems may harness these forces as energy for biological functions. Several years ago, we meticulously analyzed the energy from these sources and concluded that neither is sufficiently robust or efficient to satisfy the energy requirements of a living system, particularly in comparison to the previously discussed energy sources. While they are improbable contributors to Europa's ecosystem, we referenced them to respect the book's ethos of maintaining an open-minded approach to all possibilities not dismissed by science or logic. Subsequent conjectures are predicated on the assumption that creatures may have evolved into diverse forms, each optimizing energy utilization. Various forms of energy. An organism's energy source is often firmly embedded in its lineage, making its method of energy extraction a distinguishing characteristic for an entire category of living entities. Consequently, we shall categorize our hypothetical species based on an energy-centric taxonomy. Organisms that obtain energy from abiotic resources in the environment are producers at the lowest trophic level. They will receive priority consideration. Phototrophs. Organisms that utilize sunlight for metabolic energy would be confined to the near-surface environment. The illumination at Jupiter's distance is feeble. Surface temperatures are extremely low, and the limitations imposed by ice on the dimensions of such organisms, which presumably reside in small to minute inclusions, suggest that they would predominantly be slow-growing microorganisms. Inclusions in the surface ice may harbor living organisms, sustained by chemical reactions involving hydrogen reduction, produced during the decomposition of water. For the same reasons previously mentioned, they are likely slow-growing microorganisms. We shall designate them as radiolytic chemotrophs. We have delineated various chemical reactions that may transpire in Europa's subsurface ocean. The quantity of creatures capable of flourishing from these reactions is at least equivalent to the processes themselves. Chemolithotrophs, litho equals rock, may thrive on the ocean floor's reduced iron or other metals. If the mantle emits hydrogen as the reducing agent, we shall designate them as hydrogen lithotrophs. They may be classified as sulfur lithotrophs if they obtain their reductive energy from sulfur. One of the sulfur compounds confers this property. Alternatively, organisms like Earth's methanogens thrive by transforming carbon dioxide into methane. We shall refer to them as benthic methanogens. Aerobic organisms may inhabit the ocean's surface, where oxygen availability is enhanced, increasing the likelihood of oxidation reactions. We will classify them as upper-level aerobes. These chemoautotrophs rely on widely distributed chemical substrates within the organism's surrounding environment. Organisms are likely to inhabit places with higher concentrations of substrates when there are significant gradients, such as the ascent of minerals and reducing agents from the mantle or the diffusion of oxygen through the ice at the ocean's surface. If substrates are widely distributed in horizontal layers, organisms would lack the motivation to traverse in quest for their chemical nutrients. A horizontally compressed mat of sessile organisms is the most probable configuration for these entities. Consequently, mats of benthic lithotrophs and methanogens may blanket the ocean floor, while various upper-level aerobes reside in the higher strata. Kinetotrophs necessitate adhesion to a solid substrate to maintain their trajectory. This enables them to absorb the maximum convective energy. Delicate organology. Slender or elongated, resembling reeds, may be affixed to the substrate. Electric currents traversing specific molecules impart tensile potential energy as they deform. These molecules then utilize their stored energy to facilitate processes that enhance metabolism. We shall refer to them as benthic reeds. Ciliated organisms can harness kinetic energy through an alternative mechanism. Tensile deformation at the cilia's base converts into potential chemical energy as the cilia flex in response to the flowing stream. The cilia can assume a pancake-like configuration, either falling to the ocean floor, benthic ciliates, or ascending to the surface, sealing ciliates. Osmotrophs and ionotrophs. Living organisms must be capable of traversing between regions of elevated and diminished solute concentrations to utilize the potential energy provided by ionic and/or osmotic gradients. 8.4. The distance should be minimal given the strong concentration gradients at both the ocean floor and surface. Predicting the size and morphology of these species is challenging due to the influence of two opposing selective pressures during their evolution. A substantial surface area relative to volume would increase the number of ionic or osmotic channels per organism. A greater organismal volume would provide a more effective buffer against the fluctuations in concentrations caused by the influx of ions or water. Maximum surface area necessitates maintaining the organism in a compact, flattened form, whereas maximum volume requires the organism to remain huge and spherical. Evolution may explore both possibilities, wherein Europa might support microionotrophs and mega-osmotrophs. Thermotrophs. If thermal vents exist on the seabed of Europa's ocean, they may support a biotic population as abundant and varied as that seen at Earth's thermal vents. These vents can absorb heat through at least two mechanisms. A spherical organism may assimilate hot water at the vent's aperture, drifting to a cooler area, where the released heat enhances the potential energy of molecules via high-energy interactions or structural conformational alterations. This will be classified as a bubble thermotroph. A lengthy structure could transport hot water vacuoles from the initial point at the collinear to the terminal point of the collinear structure. Heat transfers to the cooler surroundings at this juncture, imparting energy to appropriately configured molecules or chemical bonds. Unicellular photoautotrophs can assist heterotrophs such as benthic and thermotrophs, and they may also serve as a food source for parasites or symbionts residing on or within their hosts. Numerous cohabitants would be diminutive and immobile, akin to algae and lichens and parasitic protists in animals that remain integrated into their host environments. However, if nutrients are plentiful, they may grow significantly, resembling tree fungus or intestinal parasites. Consequently, we can categorize them according to size and host, such as megachemotrophic suckers or microthermotrophic scum. The stationary producers may provide sustenance for small motile species, such as snails that graze on the biofilm of bacteria, protists, and smaller metazoans residing on the substrate. Assuming organic coatings envelop both the ceiling and the floor, we might differentiate between benthic and ceiling scrapers. Mobile producers, such as the benthic ionotroph, ceiling osmotroph, or bubble thermotroph, may prey on mobile and pelagic predators. Active swimmers like tiny fish and floating organisms like jellyfish are metaphors for Earth's waters. We shall designate them as mobile catchers and flotation catchers. We also imagine fan-shaped structures similar to the fan coral in Earth's marine ecosystems. We could affix them to the ocean floor, positioning their planar surfaces perpendicular to the flow of tidal currents. This direction would enhance their capacity to collect microscopic creatures and trash transported by the stream. We shall refer to them as floor fans. These primary consumers may be hunted by larger, albeit fewer, secondary consumers, analogous to how huge fish prey on smaller fish. The number of predators may equal the variety of prey. For the sake of simplicity, we will categorize them as tertiary separators. Your environment comprises decomposers, a kind of consumers that subsist on dead and decomposing organic matter. Upon species demise, they descend to the ocean floor, where detritivores, varying from diminutive bacteria to lobster-like creatures, decompose them. Consequently, detritivores typically congregate on the ocean floor. Thus, they will be referred to as benthic microscavengers or benthic detritivores. Scavengers, detritivores, and ceiling detritivores may consume the European biota. Europa's history can be categorized into two principal phases. 1. An early phase of indeterminate duration, likely brief, characterized by the formation of a solid silicate mantle encasing a solidified metallic core with liquid water enveloping the surface. And 2. A subsequent, prolonged phase that persists to the present, marked by a frozen surface, beneath which lies a layer of liquid water above the solid mantle and beneath the outer icy crust. In the initial phase, residual heat from the satellite's formation would have induced sufficient evaporation from the liquid ocean to create a water vapor atmosphere. The substantial radiation from Jupiter, and to a lesser degree the Sun, would have produced more oxygen via the radiolytic decomposition of water molecules than what occurred in Earth's primordial atmosphere. Subsequently, as the ocean solidified, sporadic significant impacts could have melted the frigid oceanic crust, rapidly generating a freshwater vapor atmosphere that evaporated as the ocean surface refroze. Considering this planetary history, we have delineated a potential evolutionary trajectory for hypothetical life on Europa. The evolutionary stages mentioned below correspond to the numbers in the picture. When the global ocean was in a liquid state, accretion generated substantial heat, and organic compounds from the circumstellar disk and meteorites were readily available, There is no reason to question the possibility that life may have originated in this initial phase. Primitive life forms were basic chemoheterotrophs that used accessible organic substances for sustenance. Subsequently, additional energy-based processes may have emerged, such as the reduction of iron by. Under an early water vapor atmosphere, sunlight would have been sufficiently intense at the ocean's surface to promote the evolution of primitive organisms that obtain energy through photosynthesis. A photoautotroph could have evolved into more sophisticated cellular structures like algae. Large osmotrophs or microbial ionotrophs, step 9, may have derived their energy from osmotic and ionic gradients. Thermal emissions from the oceanic substrate may have facilitated various osmotrophs. After the earliest producers had developed, they may have provided sustenance for a primordial main consumer. The emergence of higher-order consumers may have proliferated from these original basic consumers. Once the ice shell solidified, two separate interfaces with water would have been accessible for colonization. Under the ocean's surface ice, a water-ice contact would offer a solid substrate, while the ocean floor would establish a water rock or sand connection. The vertical separation between the two is expected to be tens, if not hundreds, of kilometers, rendering the two ecosystems independent biospheres. After the formation of the ice shell, creatures resembling algae may have remained enough near the surface to obtain nourishment from sunlight or to undergo radioactive decomposition of hydrogen to synthesize high-energy molecules. A new producer form may have developed to extract kinetic energy from water currents at the roof or ocean floor. Variations on this theme may have included reed-like organisms or filter-feeding, fan-like organisms. A progenitor of the heterotrophic producer may have been an anaerobe, which subsequently evolved into an aerobic organism that utilizes oxygen near the surface. Certain forms of life may have persisted in a tertiary, smaller biosphere. This may have occurred in liquid inclusions, cryptobiotic, or on the surface, term surface face, where water emerging from underneath or bolide impacts from above might generate transient pools of liquid above the ice in a water vapor environment. A diverse array of creatures now flourishes on the ocean bottom and ceiling, enabling consumers capable of scraping them from these surfaces and various parasitic or commensal species to persist. A floating lifestyle would have developed around the ceiling and floor. Progeny of these passive feeders would have led to the emergence of bigger variants. Mobile customers may have emerged, resulting in elevated predictions and levels. Detritivores have emerged to consume decomposed matter accumulated on the ocean floor or throughout the oceanic depths up to the surface. We assume that all living types depicted have persisted to the current day. The trophic structure of the system delineates the flow of energy within it. A basic multi-level ecosystem comprised exclusively of producers that extract energy from the environment by assimilating carbon dioxide and utilizing hydrogen released from the surroundings. Trophic regions correspond to the biomass of each trophic level. As elucidated in Chapter 3, each successive trophic level possesses diminished biomass compared to the preceding level due to the inefficiency of energy transfer, which is significantly below 100%. The energy conversion efficiency of species on Europa remains undetermined, as previously calculated. The minimum size a live organism can attain remains uncertain. However, asserting that it is likely minuscule, particularly about the products found on Europa, is reasonable. This is inaccurate on Earth, where ample sunshine facilitates the substantial growth of vegetation. Nevertheless, microorganisms in the ocean's upper strata account for most of Earth's overall biological productivity. Massive producers might inhabit the region if a highly abundant energy source exists on Europa, and animals have evolved to exploit it greatly. Although assurance is unattainable, most energy sources are less conducive to effective capture than sunlight, making it plausible to anticipate that the overall energy production on Europa will be very modest. The overall energy available dictates the total biomass that can be sustained. Formulating logical assumptions on the dimensions of animals at each trophic level in similar marine habitats on Earth allows us to approximate the quantities and sizes of organisms at each trophic level in model ecosystems for Europa. We have endeavored to simulate Europa's energy availability and consequent biomass. The calculations are complicated and replete with assumptions that are merely educated conjectures based on our present understanding. The outcomes of these simulations are informative in shaping our understanding of the characteristics and boundaries of potential life on Europa. Christopher Chiber and Cynthia Phillips of the SETI Institute have presented a model ecosystem predicated on radiolytic oxygen generation at Europa's surface. Researchers determined that a tertiary consumer weighing around 1 gram, comparable to a tadpole, may inhabit every 6.76 cubic meters of water on Europa, contingent upon the influx of oxygen into the subsurface ocean beneath the ice. This would occur if we distributed the biomass uniformly around the ocean. We have proposed a model ecosystem centered on methanogenic producers that generate biomass comparable to that of tertiary consumers over every 32.5 centimeters of the ocean, corresponding to a boundary length of 5.7 meters. Mikhail Zolotov and Everett Schock have presented a third model ecosystem that utilizes anaerobic sulfate reduction as an energy source. Their findings indicate a tertiary consumer in 729 cubic kilometers of water, equivalent to a cube with edges measuring 27 kilometers. The varying anticipated densities for apex creatures in Europa's oceans stem from differing assumptions regarding producers' energy acquisition methods. We are uncertain which of these models' methodologies are feasible. They facilitate the visualization of possibilities, including the limitations on support for each environment. It appears improbable that animals the size of tadpoles, dispersed over an average distance of 27 kilometers, as proposed in the model of Zolotov and Schock, constitute a viable population. Conversely, the same creatures might interact easily at an average distance of 5.7 meters, around the length of a household swimming pool. Having identified habitats and probable energy sources and enumerated a conceivable array of creatures, we can conceptualize the biotic communities on Europa. There exist 3 distinct life zones. The initial and most conjectural hypothesis posits a colony of creatures near the ice's outer surface. The other 2, probable if life is discovered in the subterranean ocean, reside at the interface between the sea surface, the roofline, and the boundary between the ocean floor and the mantle. The extreme radiation and harsh cold on Europa's surface pose significant hurdles to unprotected organisms. Nonetheless, it is plausible that a stratum of phototrophic organisms may reside within minor liquid inclusions in the ice, just a few millimeters from the surface. We possess additional non-phototrophic, phototrophic, and non-phototrophic organisms, influenced by hydrogen ion gradients produced by radiative surfaces. The minuscule dimensions of the inclusions would restrict the organisms to microbial size, and their access to energy sources would be confined to horizontal layers next to, but not at, the ice surface. Cross-sections of ice cores would display this community as horizontal strata. Upon encountering ice, we may observe a proliferation of mats and film ciliates, ciliated organisms that necessitate adhesion to a substrate. Grazing among these flat populations would involve snail-like scraping, snail-like detritivores, and various symbionts. The organisms near the roof may be somatotrophs, varying in size based on their adaptations for navigating the salinity gradient. The ocean floor may resemble this, featuring mats and films that blanket the whole horizontal substrate, predominantly composed of chemoautotrophs. A diverse array of symbionts, consumers and decomposers could contribute significantly to the organismal diversity of this benthic community. Ionotrophs, suspended above the ocean, can absorb ions from the seabed and release them into the less concentrated waters above. Multiple secondary consumers may be swimming and eating on the lions. The characteristics of the organisms inhabiting the open depths between the floor and ceiling are more challenging to anticipate. Predators may utilize this area for sustenance whenever any organism enters it. The dimensions and mobility of these consumers, together with the number of trophic levels in the food chain, are ultimately contingent upon the total energy assimilated by the producers. The quantity of available energy is the most crucial piece of missing information regarding Europa. The predominant biosphere on Europa, except a superficial layer of microorganisms, would be confined deep under the satellite's surface amid constant darkness and cold. What would existence entail under metabonds? If life were to exist on Europa, it would develop and progress at a gradual pace. The diminutive dimensions of Europa's lithospheric core restrict radiogenic heating, and any energy derived from convection currents necessitates that organisms remain fixed and immobile. Significant potential exists for ionic and osmotic gradients. However, these may be absorbed by elongated creatures adhering to the surface or by delayed flotation. Organisms are anticipated to inhabit frigid environments, possess constrained energy reserves, and infrequently require autonomous locomotion. Europa's biomass is stationary and resembles that of plants, probably owing to its utilization of plant-like tactics. Predicting the significance of sexual reproduction on Europa is challenging. On one side, Europa's geological history has remained mostly unchanged since the global ocean solidified shortly after its formation. This would have prioritized stabilizing selection in the early stages of planetary history, refining the simplest and most efficient reproductive systems. This generally refers to basic fission, budding, or other vegetative methods of asexual reproduction. Conversely, parasitism had a significant role in Europa's biological dynamics. Given that several theories of sexual reproduction on Earth suggest its primary function is to mitigate parasitism's detrimental impacts, sexual reproduction may also be relevant on Europa. Nevertheless, for most of the biomass likely to remain stationary, even sexual reproduction would resemble that of plants, with reproductive cells being disseminated passively. Due to the universal availability of their energy sources, chemical, osmotic, or kinetic, at the interface between the ocean and substrate where they predominantly inhabit, motile creatures in Europa's ocean would require autonomous movement. Thermotrophs would require minimal movement, perhaps only short distances, and would do so passively from their stationary heat sources. As one progresses up the food chain, the evolutionary rivalry between predators and prey compels both to optimize their speed, akin to how evolution has driven the cheetah and elk to enhance their velocity over time. Energy availability may restrict certain life forms. Most living forms on Europa are unlikely to possess organized sensory systems. Most organisms anticipated in a deep, dark oceanic habitat would be either stationary or passive drifters. They might react to their local settings by encasing them in salt concentrations. They may also possess the capability for trophic amoeboid behavior, indicating their ability to expand or migrate toward energy sources, such as concentrations of hydrogen ions. In this respect, they are analogous to terrestrial plants and microorganisms. Conversely, sensory perception and specific assessments ensure that customers can nourish themselves. This sensory ability would exclude vision, although the power to detect electrical currents, thermal variations, and chemical substances, odors, would be advantageous. The underwater environments of Europa are expected to be devoid of sound and light, as it is improbable that huge organisms capable of long-distance acoustic communication inhabit these regions. Nonetheless, the potential exists that certain consumers may utilize sonar to detect prey or possess the ability to perceive gas bubbles originating from deep-sea vents. Sensitivity to pressure, heat, odor, and potential auditory perception would necessitate a system resembling a nervous system. Determining if animals inhabiting Europa's subsurface ocean possess cognitive abilities, absorb information, and exhibit behavioral decision-making is not very challenging. It is also not difficult to ascertain whether these organisms possess mobility and sensory capabilities. The The cognitive capacity of terrestrial animals correlates directly with the intricacy of their neural systems, which is influenced by the breadth of their sensory functions and the necessity for motor coordination. If our hypothesis that most animals in Europa's ocean are largely immobile and lack sophisticated sensory capabilities is validated, we can infer that even the most intelligent entities in that environment likely possess limited cognitive capacity. Europa may possess extraterrestrial life. Nevertheless, such intelligence is not notably sophisticated. We cannot dismiss the notion that Europa is devoid of life. Europa's mantle and core are smaller than Earth's moons, which seemingly no longer produces internal heat via radioactive decay, suggesting that Europa may lack any remaining internal heat source. No chemicals like carbon dioxide or sulfur may emanate from Europa's noemotrophic metabolism. An eruptive ocean may be present beneath the ice layer. Consequently, no currents or alternative types of kinetic energy may be accessible. Ultimately, while we may have postulated a planetary history for Europa, this is inaccurate. The duration during which the liquid water layer over the rocky core existed may have been insufficient for the emergence of life. Any of these scenarios, if accurate, would diminish the likelihood of life on Europa. The surface is youthful and active, indicating significant tidal flexing. This ensures that creatures with suitable adaptations, whether thermal, kinetic, or both, can capture energy. A robotic trip to Europa, even if limited to sampling surface chemicals and measuring geological activity, would greatly enhance our capacity to ascertain the viability of various scenarios. A dynamic, multi-layered ecology flourishing under Europa's freezing surface is more representative of its reality than a barren, frozen entity. Our discourse on the potential for life on Europa must also encompass the analogous possibilities on a more distant moon, Saturn's little icy satellite, Enceladus. Enceladus, a cryogenic moon, contradicts our anticipations in multiple respects, particularly given that a celestial body of its diminutive size, with a diameter of about 500 kilometers, ought to remain cold after 4.5 billion years since its inception. In contrast to this anticipation, Enceladus exhibits signs of recent resurfacing and radiates thermal energy from its southern pole. In November 2000, the Cassini orbiter approached within 25 kilometers of Enceladus, capturing striking images of jet-like plumes from its south pole. Upon closer examination of the South Pole, scientists observed the pronounced trenches called tiger stripes. They also found evidence indicating that the geysers and thermal activity originate from distinct fractures along these stripes, now identified as slide faults within the unyielding frozen crust. Diverse ideas exist for the energy propelling the geysers. The compositional data indicate that the geysers' contents predominantly consist of water, accompanied by methane and trace amounts of organic compounds, as well as nitrogen, carbon dioxide, and carbon monoxide. Experts today contend that Saturn's E-ring is predominantly produced by these emissions, and sodium compounds within the ring likely originate from water beneath the frozen crust, in contact with a rocky core. The potential existence of liquid water beneath Enceladus's surface and the availability of heat and possibly organic chemistry indicates a distinct similarity to Europa. Consequently, forecasts on the potential existence of life there would adhere to the same rationale and reasoning previously outlined for Europa. An unresolved issue pertains to the historical trajectory of life beneath the ice of Enceladus. During their formative period, Saturn's largest moons, Titan and Enceladus, may have possessed comparable warmth and a rather abundant array of organic compounds. The two may have exchanged rudimentary forms of life. Enceladus likely froze rapidly due to its diminutive size and significant distance from the Sun. Any genesis of life predicated on the presence of liquid water at the surface would necessitate a relatively rapid occurrence. Nonetheless, considering Enceladus has contradicted traditional assumptions, we should not exclude this possibility. If life had originated or been introduced in Enceladus's primordial period, the biosphere could have remained uncomplicated and mostly unchanged when the surface solidified. Europa holds a prominent status in the considerations of astrobiologists for three reasons. Initially, our solar system serves as a reference. In that case, Europa may represent a more typical planetary body in the cosmos than our inner rocky planets or gas giants. As little icy planetoids are the most prevalent entities in our spatial vicinity. Secondly, Europa possesses abundant water and is likely to harbor life forms that human explorers are better equipped to identify. The early life forms on Europa, possessing a planetary history reminiscent of Earth's formative period, may exhibit similarities to our primordial organisms, despite their largely distinct origins. Ultimately, a planet possessing an ice-covered ocean and a distinct interior can support a multitude of diverse habitats. This indicates that numerous energy sources and diverse environments are crucial for fostering biological variety, as evidenced by the history of life on Earth. Based solely on this assessment, Europa presents a superior potential for biodiversity compared to any location in our solar system, with the probable exceptions of Titan and Triton. Enceladus's diminutive size and increased distance make it less probable to harbor life compared to Europa. The unforeseen geophysical activity in that region makes us doubt established beliefs. Evidence of life on Enceladus strongly indicates that life will likely exist on several additional celestial bodies inside our solar system. Europa is the most probable location in our solar system, beyond Earth, that may sustain a somewhat complex biosphere comprising life forms similar to those we recognize. It has a substantial subterranean ocean of liquid water and several energy sources. Although the chemical richness of the oceanic ecosystem remains uncertain, there is no reason to question the potential presence of organic chemistry precursors. A fragile oxygen atmosphere also envelops the ocean's ice shell and may contribute to the subsurface habitat. Light holds no biological utility on Europa, save for a limited number of ice-encased creatures at the surface. A multitude of kilometers of light-obscuring ice envelops all other life forms. Energy can originate from various sources beneath the ice, including chemical reactions, heat emissions from within, water currents, and ionic or osmotic gradients generated by the ocean floor or ice ceiling, respectively. Diverse producers utilizing any or all of these energy sources might form the foundation of a food chain capable of attaining considerable complexity. Feasible models have been suggested that depict ecosystems reaching the level of tertiary consumers, with species comparable in size to the small to medium-sized marine fauna known on Earth. Life on Europa is expected to be predominantly sedentary, characterized by minimal mobility due to frigid conditions and restricted energy availability. This implies rudimentary sensory systems and restricted cognitive abilities. The reproductive tactics would likely be straightforward, emphasizing the sexual exchange of genetic material. We could have preferred to neutralize the entrance of parasites. Researchers are keen to investigate extraterrestrial life due to 1. Europa's potential significance among the planets in the universe, 2. its capacity to sustain water-based life forms, which may resemble those on Earth, and 3. its distinct demarcations between water, ice, atmosphere, and substrate, facilitating the habitat fragmentation essential for the emergence of complex biospheres. The potential for significant biodiversity in Europa is comparable to any known extraterrestrial world. Finally, the little icy realm of Enceladus is briefly examined. The water jets emanating from its southern pole indicate the presence of a substantial oceanic reserve beneath the surface, akin to that of Europa. The discussions in this chapter regarding Europa would similarly pertain to Enceladus, contingent upon confirmation. Existence at the juncture of volcanic heat and icy terrain on a tumultuous sulfur-laden lake. La Morabito had graduated with a degree in astronomy 4 years prior when she assumed the role of navigation engineer for the Voyager expedition. On March 5, 1979, Voyager 1 executed its nearest approach to Io, capturing images that unveiled a celestial body unprecedented in the solar system. Linda's responsibility was to accurately determine the positions of Voyager's target planets and moons relative to the stellar backdrop observed from the spacecraft, ensuring it remained on its correct trajectory. On the morning of March 9th, she was augmenting the contrast of an image captured the prior day to better discern the weak stars obscured by Io, when a crescent-shaped object appeared in the top left edge of the moon. Recognizing that such a substantial object could not be another moon in that location, she comprehended that she might be witnessing something unprecedented. Reflecting on the discovery years later, the excitement had not diminished. It seems inconceivable that such a substantial object had ever gone unnoticed. It was a moment anticipated by every astronomer and planetary scientist. Those instances were genuinely remarkable. For the subsequent 6 hours, Linda and her colleagues examined every logical rationale for the abnormal image, until only one possibility persisted. The crescent shape and the luminous region at the terminator, the demarcation between light and shadow, are likely attributable to surface phenomena on Io. Months prior, Stanton Peele and his associates at the University of California, Santa Barbara, had disseminated a forecast indicating that Io should exhibit volcanic activity. It became increasingly evident that Linda had observed the nebulous plume of a substantial volcanic eruption. During supper that evening with her parents, her father remarked, "Are you aware that you might have identified the first volcanic activity beyond Earth?" Her discovery significantly affected her. "It was delightful to hear him express that," Linda reminisced. Linda Morabito's father disclosed the discovery shortly thereafter, and science validated and published it on June 1st, 1979. For numerous planetary scientists, this constitutes the most significant finding of the Voyager mission. To this day, volcanism defines Io. Any process or phenomenon associated with that satellite, including its astrobiological potential, begins with acknowledging that Io is the most volcanically active, celestial body known to humanity in the universe. Io is a casualty of its environment. Throughout its existence, it has endured numerous meteorite impacts, intense magnetic fields, and significant gravitational stress, surpassing that experienced by any other celestial body. This predicament arises from its proximity to Jupiter and position between Jupiter and 3 substantial companions. It anticipates insights regarding exoplanets in close orbits around their central stars. We can closely monitor its daily challenges to evaluate the boundaries of life's adaptability. Io is the densest of the major moons in the solar system, resembling a rocky planet more than any other satellite. It possesses an iron or iron silicate core that constitutes approximately 1/3 to 1/2 of its radius. Like the rocky planets, silicates predominantly comprise the remaining material. With a density significantly lower than Earth's density, suggesting the presence of substantial liquid beneath or within the crust, which is estimated to be up to 11 kilometers thick. 3 energy sources account for Io's internal heat. Firstly, the core's substantial size allows for ongoing radioactive decay, which generates thermal energy. Since Io's formation, heat has accumulated due to bolide impacts. As the closest of Jupiter's 4 major moons, it is situated at the terminus of the funnel that attracts in-falling bodies towards a collision with Jupiter. Consequently, Io has likely intercepted a disproportionate number of impactors. The heavily cratered surface of Callisto, the most remote Jovian moon, illustrates the significantly greater bombardment Io has experienced throughout its history. The predominant heat source on Io is gravitational flexing, resulting from its position between the massive Jupiter and its 3 neighboring moons. When Io is positioned opposite Jupiter from the other moons, it experiences gravitational attraction solely towards them. Conversely, Io stretches in both directions between Jupiter and its siblings, particularly Europa and Ganymede. Scientists estimate that the amplitude of the rigid crust's expansions and contractions can reach up to 100 meters. Given that Io completes an orbit around Jupiter every 1.77 days, in a 2-to-1 resonance with Europa's 3.55-day orbital period, the surface experiences crustal tides approximately every 43 hours, excluding Ganymede's influence. These variations induce internal friction, perpetuating a continuous state of thermal agitation within its interior. Volcanic activity is consistently observable on Io, with 1 to 2 dozen active eruptions, enough massive to be seen from orbit, occurring at any moment. Linda Morabito initially observed the significant plumes expelled with considerable force at approximately 1 kilometer per second velocities. This phenomenon results in sulfur dioxide, SO2, fountains, and other volatile gases ascending to altitudes of up to 300 kilometers, before descending to the surface in concentric rings, akin to the red circle surrounding Pele. These plumes are believed to be produced by elevated subsurface pressures that maintain sulfur dioxide and other volatile gases in a liquid state, until a breach in the surface creates an escape route. Plumes are generated by the gradual movement of lava across sulfur dioxide snowfields. Low temperatures cause erupting lava to solidify rapidly at the surface, resulting in the slow migration of the liquid edge of the eruption. Models indicate that the subterranean magma reservoirs may be rootless, lacking a singular conduit to the surface. Extremely hot lava melts the crust it traverses, forming a boundary layer slurry that vaporizes as the erupting seam progresses slowly across sulfur dioxide fields, producing wandering plumes. The expanding lava ultimately forms extensive lava fields, crusted lava lakes, and calderas due to the depletion of substantial underground reservoirs. The elevated temperatures nearing 1700 degrees Celsius recorded during these eruptions align with magnesium-rich silicates and a significant quantity of sulfur compounds. The volume of ejected material is substantial. The Amirani lava field, extending over 300 kilometers, has been produced by lava expelled at an estimated rate of 100 tons per second. The relative scarcity of large volcanic mountains on Io indicates that the lava possesses low viscosity, consistent with a high liquid content. Io's atmosphere is exceedingly sparse. It is principally composed of sulfur dioxide, SO2, with trace amounts of sulfur monoxide, SO, hydrogen sulfide, H2S, carbon monoxide, CO, and carbon dioxide, CO2. It remains uncertain whether atmospheric SO2 originates chiefly from the evaporation of surface, SO2, or from direct volcanic emissions of SO2. Analogues of these compounds are present in Io's ionosphere. The powerful magnetic field of Jupiter likely produces these compounds by removing electrons from their parent molecules. The surface of Io consists of silicate and sulfur compounds, enveloped by a layer of condensed SO2. It is posited that different sulfur compounds have a role in the echinotechny coloration. The predominant white hue of the surface is attributed to condensed SO2. Notwithstanding Io's intense bombardment, its surface remains consistently youthful because of ongoing volcanic activity that rejuvenates it. No celestial body in the solar system has undergone as many transformations as frequently as Io. Distinct boundaries are ubiquitous. Expansive lava fields, multi-tiered calderas, and slender channels intersect vast level plains on a grand scale. Recently paved regions overlay older solidified flows with greater detail, occasionally abutting flat, undulating plains compressed by enigmatic forces. Except several shield volcanoes, the mountains on Io are not of volcanic origin. They are formed through uplift along thrust fault lines caused by compressional forces within the interior. Jagged crustal blocks ascend from the adjacent flat plains. Gorges that traverse these mountains are believed to offer further evidence of these fault lines, although erosional forces from flowing lava also play a role. Extensive evidence of sapping is seen, 9.3. Additionally, we find elongated channels that may arise from either sapping or liquid flow. Since no liquids can remain stable at the temperature and pressure conditions on Io's surface, any liquid flows must predominantly consist of lava. The intrinsic surface temperature of Io, excluding areas of volcanic activity, is approximately 90 degrees Kelvin, minus 183 degrees Celsius. This extremely low temperature indicates Io's distance from the Sun and its minimal atmospheric presence. Due to volcanic activity, numerous hotspots exist on Io's surface, with temperatures increasing in concentric gradients towards them. At Loki Patera, Io's most active volcano, temperatures approach 0 degrees Celsius, the melting point of water ice, at the edge of an oval measuring 50 kilometers long. Within several kilometers of the hotspot, surface temperatures can reach 47 degrees Celsius, while at the site of magma eruption, temperatures may soar to 2000 degrees Celsius. The thermal gradients generated at the surface can be extensive, spanning significant distances or highly compressed. At Loki Patera, for instance, the surface temperature varies from 280 degrees Kelvin, 7 degrees Celsius, to 320 degrees Kelvin, 47 degrees Celsius, over approximately 32 kilometers, 20 miles, to the left of the peak. Conversely, the same transition occurs much more abruptly, over a distance of about 1 kilometer to the right of the peak. Similar gradients likely exist underneath. However, they have not been measured. Intense thermal gradients will be produced as lava, exceeding 1,500 degrees Celsius, flows over a snowfield of frozen sulfur dioxide at minus 80 degrees Celsius. Observations indicate that this movement progresses several centimeters daily. Consequently, the gradient advances gradually. The lava fields may endure for extended periods. Once the surface solidifies, insulating the molten lava beneath, the underlying ground will be heated, and the peripheries of the field will sustain a notable thermal gradient for a considerable duration. Both horizontal and vertical gradients will exhibit a continuously evolving profile. Io revolves within Jupiter's magnetosphere, which generates and subsequently removes ions from Io's ionosphere. Jupiter's swift rotation of its gravitational field produces intense currents, estimated at 1,000 gigawatts, yielding a potential electromotive force of 400 kilovolts. These ions possess strong oxidizing properties, facilitating oxidation-reduction cycles. Nevertheless, most of these ions likely reside in the ionosphere, where they are rapidly stripped away by Jupiter's rotating magnetosphere, thus casting doubt on their contribution to surface oxidation-reduction cycles. Electromagnetism and electricity signify potential energy sources, perhaps to a greater extent on Io than in any other location inside the solar system, excluding the atmospheres of the gas giant planets. The amalgamation of metals and silicates likely solidified from analogous material, constituting a significantly larger core at Jupiter's center. Due to its proximity to Jupiter and location within the orbits of other nearby satellites, gravitational flexing would have predominantly influenced Io's characteristics from the outset. Jupiter's substantial gravitational field rapidly attracted hydrogen and helium to Io's diminutive core. Nevertheless, its core was sufficiently large to retain water, which it may have possessed briefly during its formative stages. The water was lost relatively quickly due to sublimation, vaporization from persistent volcanic activity, and intense bombardment by bolides drawn into Jupiter's dense gravitational well. Despite the continuous emission of volatile gases from Io's interior, the formation of an atmosphere in its early stages would have been impeded by intense magnetic and radiation fields and frequent bolide impacts. Io maintains only a tenuous atmosphere composed primarily of sulfur dioxide and trace quantities of other volatiles. Absent the thermal insulation an atmosphere provides, Io's surface temperature plummeted to approximately minus 180 degrees Celsius early in its history. Nevertheless, the interior has persisted in generating heat due to friction from gravitational flexing, which is subsequently conducted to the surface through localized and dynamic outlets. There is no reason to question that Io's vibrant hues existed long before the human eye evolved to perceive them. Io's surface has likely continuously transformed for at least 1 billion years, as molten lava traverses an icy layer of silicates and frozen SO2. The contrast between fire and ice transcends mere metaphor for Io. The fundamental nature of life there hinges on the interaction between heat and cold, representing the extremes that establish a boundary. Varying in thickness from millimeters to kilometers, between a frigid substrate too cold for any liquid and a layer of disseminating heat that renders the retention of nearly any liquid unfeasible. Life may flourish briefly when a temporary equilibrium between fire and ice exists between intense heat and the frozen substrate. Life flourishes at interfaces, between air and surface, sea and shore, and ocean floor. Extremophils particularly thrive at the junctures of extremes. Yellowstone National Park exemplifies this phenomenon. Although analogous locations exist globally, the park's abundant geysers, fumaroles, and thermal pools illustrate excessively hot, acidic, or alkaline environments for organisms accustomed to more temperate conditions. Nevertheless, certain extremophiles flourish in these harsh conditions and cannot survive outside them. Merely a few centimeters from the scalding water, these extremophiles are supplanted by other life forms compatible with the more temperate conditions above or beyond the water's edge. Multiple gradations of life can frequently be observed within 1 to 2 meters. Wherever gradients are formed, particular life forms occupy their suitable niches. This is evident in vertical and horizontal transitions, as seen by a cliff exposing successive soil layers, 9.10. Many individuals believe that life may thrive on Earth. Bruce Jakosky, a planetary scientist at the University of Colorado, articulates a common perspective. The most reasonable conclusion is that, in 1998, he stated that Io possesses neither water nor life. No evidence exists for a minimal quantity of water on Io. However, it is merely a trace and insufficient to sustain water-based life. Could alternative solvents exist within the dynamic gradients on Io? Are there adequate conditions for life that could contest the prevailing notion that life on Io is improbable? Let us explore the possibilities. Sulfur dioxide and hydrogen sulfide exhibit high solubility in water. Subsurface water may exist as a liquid near geothermal hotspots, or lava flows if concentrated solutions of these gases, primarily diluted sulfurous and sulfuric acid, are present, thereby reducing the melting point of water. Nevertheless, the minimal water on the surface indicates that water is an improbable solvent for any substances on Io. Sulfur dioxide presents a more favorable option. It is plentiful in its frozen form on the surface, but transitions to a liquid state underground at temperatures ranging from -75 degrees Celsius to -10 degrees Celsius. This corresponds to approximately the 200 degrees Kelvin to 260 degrees Kelvin isobars in Figure 9.8b, covering extensive areas, essentially the dark terrain in the image, on the right slope of Loki Patera. Although the low vapor pressure at the surface would lead to rapid vaporization, subterranean CO2 remains liquid, under pressure, in stable reservoirs. Hydrogen sulfide may theoretically function as a solvent, with a liquid temperature range of -85 degrees Celsius to -60 degrees Celsius. Consequently, it might exist as a liquid underground in a geothermal hotspot. Nevertheless, its surface abundance is considerably lower than that of SO2, which seems to be a more prevalent solvent. This scenario may arise when the solvent in the surrounding environment diverges from the liquid medium in which metabolic processes transpire. While SO2 can engage in biochemical interactions, it is not an optimal solvent due to its limited capacity to form hydrogen bonds and inability to facilitate the conformational changes of macromolecules essential for their functions. Conversely, hydrogen sulfide possesses these advantageous properties but is significantly less prevalent. Nevertheless, its liquid range -60 degrees Celsius to -85 degrees Celsius coincides with that of sulfur dioxide. Living cells could utilize TSO ore as a solvent internally while existing in an environment predominantly composed of liquid SO2. Any potential basis for life on Io would necessitate the ability to synthesize complex biomolecules capable of sustaining metabolic processes in liquid sulfur dioxide or sulfur dioxide sulfide at 180 degrees Celsius, temperatures ranging from -50 degrees to -70 degrees Celsius. Our understanding of the biochemistry of carbon-based polymers under such extreme conditions, which diverge significantly from the water-based biochemistry at elevated temperatures that we are accustomed to, is insufficient to ascertain whether life on Io could be constituted from carbon backbone compounds. Currently, there is no evidence of organic compounds, and the presence of carbon is minimal, limited to trace amounts of CO and CO2 in Io's atmosphere and frozen substrate. Sulfur is, undoubtedly, highly abundant. One of sulfur's most appealing characteristics as a prospective constituent of biomolecules is its ability to adopt numerous oxidation states, including fractional ones. This enables sulfur to build a wide array of compounds. Sulfur exhibits several ring configurations, some of which contribute to the vibrant colors of Io's surface. Upon delving beyond the surface and combining liquid SO2 and SO22, one may encounter chemical intricacies involving sulfur rings or polymers. Polymers composed of carbon, sulfur, nitrogen, oxygen, and phosphorus may give rise to biomolecules similar to those found in living cells on Earth. Nevertheless, we lack confirmation of their existence and possess minimal data regarding the possibilities under Ionian settings. Similar to several domains within astrobiology, empirical investigations conducted in terrestrial chemical laboratories contribute to the hypothesis that this energy type may surpass all others as it is observable in motion. It is abundant, and the contrasting freezing ambient temperatures create a readily available sink, ensuring heat transfer from its source. As indicated in Chapter 2, energy traversing a system typically facilitates its organization. Although heat is readily dissipated as increasing entropy, rendering it highly inefficient, its abundant availability on Io could facilitate the existence of life there. A notable source of energy is energy iodation reduction chemistry. The predominant element on Io, sulfur, is present in an oxidized state as sulfur dioxide, in a neutral state as sulfur and sulfur X, and in a reduced state as hydrogen sulfide. Therefore, sulfur theoretically possesses the capacity for oxidation reduction cycling. The thermodynamic reality, whether ionization and reduction events can occur in a manner that generates energy, indicates that mechanisms have developed to link with these reactions to harness that energy in a biologically utilizable form or substance. We once again depend on the creativity of evolution. Organisms adjust to their surroundings, and the history of life on Earth illustrates that evolution is as innovative as our imaginations. For the first time, a third energy source must be carefully examined in the context of Io. That pertains to electromagnetism. As previously mentioned, Io traverses Jupiter within the confines of that planet's Magnetosphere. Although the energy derived from electromagnetism is typically less competitive than chemical or light energy on Earth, Jupiter's magnetic field is at least 12 times stronger than that of Earth, and sunlight is 25 times weaker, suggesting that magnetism could potentially energize a suitably designed biological process on Io. The perpetual spinning of Jupiter's magnetosphere along Io's orbital trajectory may also provide electricity. Organisms on Earth have evolved to perceive magnetic fields and electric currents. Since sensation is merely the identification of energy fluctuations in a biologically significant manner, it follows logically that energy fluctuations can influence biological processes. Biological organisms may capture energy by linking it to a storage device. In contrast to the other planetary bodies we have examined, Mars, Venus, and Earth, where the emergence of life was more conceivable than its continuation, Io poses a significant difficulty. A modern microorganism might easily remain in a state of cryptobiotic hibernation within a frozen substrate until an above-lava flow melts its subterranean environment, thereby reviving it. It is far more challenging to comprehend how that bacteria could have initially originated. The issue is that our knowledge of the initial phases of Io's existence is exceedingly limited. The evidence suggests that it could not retain significant water for an extended duration, or possess an atmosphere for more than a fleeting interval, before being overwhelmed by relentless impacts from celestial bodies and substantial gravitational distortions. It is tempting to conclude that conditions have become excessively arid, frigid, and rapid for the gradual mechanisms associated with the emergence of life in aquatic environments to unfold. We are uncertain about the duration required for life to commence in an abstract context, and we do not know if the conditions conducive to the origin of life on Io persisted for a sufficient duration. What if water were ephemeral or perhaps non-existent? Life emerged in frigid lakes of sulfur dioxide. Sulfur dioxide may have been dispersed throughout the surface during a primordial phase of Io's existence under a sparse atmosphere. While we cannot dismiss the notion, we lack facts and compelling models to substantiate it. Given our ignorance regarding the origin of life on Earth, the acknowledgement of our uncertainty about its potential inception on Io should not be perceived as a critical deficiency. This book focuses on potentialities rather than historical realities. Hence, we shall now posit that life could have emerged on Io despite the tumult and bloodshed surrounding the satellite's formation. Any surface habitats that may have been conducive to life on Io were likely ephemeral. Researchers postulate that Io and Europa originated at temperatures of -23 degrees Celsius, or above, 8. This indicates that the surface may have contained pools of liquid sulfur dioxide and sulfur dioxide 22 sulfur LOH2 sulfur, following the freezing of any water, provided there was sufficient atmospheric pressure to impede evaporation. These pools may have persisted sufficiently for life to develop within them, maybe on the substrate at the bottom or in little puddles where evaporation concentrated essential reactants. Once the atmosphere was removed by Jupiter's formidable magnetosphere or eroded by initial bombardment, the pools would have either evaporated or frozen as they adjusted to the planet's global average surface temperature. Below the surface, where temperatures are elevated and pressure is intensified, specific strata would maintain temperatures between -10 degrees Celsius and 5 degrees Celsius, suitable for retaining sulfur dioxide in a liquid form. Silicates, frozen SO2, and other volatiles in the overlaying crust formed a rigid, frigid surface. Periodically, flowing sheets of lava would traverse the frozen terrain, temporarily melting it and transforming it into a mushy amalgamation of minerals and solvents. Upon the lava's solidification and its heat's dissipation, an interval that may range from minutes to centuries, contingent upon the volume of lava above, it would return to its frozen state. It possesses two primary categories of habitats. One consists of relatively stable subterranean reservoirs, predominantly containing sulfur dioxide, while the other consists of transient mixtures of soil and liquid that liquefy at the interface of severe temperatures, such as where geothermal hotspots or flowing lava encounter frozen terrain. Ultimately, the Earth will solidify once more. The duration for which these two habitats have existed as the sole environments on Io remains uncertain, but they have presumably been conducive to life since their inception. Consequently, our conjectural path for evolution on Io pertains to a singular geological condition that has persisted from the inception of life on that celestial globe. The probability of that occurring is minimal, A meteorite may have embedded MS in Europa's icy crust and ejected it from the satellite. Even if the ice fragment were sufficiently large to withstand the blast that propelled it, which is dubious, the Europan life, upon reaching Io, would encounter an environment so vastly different from its origin that survival in the realm of fire and ice seems exceedingly unlikely. For this hypothetical history, let us posit that life originated on Io, in or beneath a pool of liquid sulfur dioxide. There may have been sufficient H2S to facilitate more intricate chemical reactions in a secure environment, resulting in the emergence of the first cells. The initial stages of life probably utilized chemicals condensed in ice inclusions or adhered to solid substrates as foundational elements and energy barriers. They also synthesized the bigger molecules necessary for complete life. They would have been ancestral chemoheterotrophs, in other words. Chemotrophs fully developed and capable of consistent self-replication may have emerged on substrates under the liquid, step 1, and within small cavities in the SO2 ice above or adjacent to those substrates, step 2. Given the abundance of thermal energy, an ancestral substrate thermotroph would have utilized this energy source, step 3. Free-floating chemotrophs, step 4, evolved from forebears embedded in ice inclusions. Despite our repeated observations that heat is not an efficient foundation for bioenergetics, its plentiful presence at the peripheries of heat sources, such as spreading lava fields, compels us to contemplate a potential form of life on Io that may have evolved to rely on it. Step 5. Free-floating thermographs absorb heat from a source, such as a substrate, and subsequently utilize that heat to reduce the substance to a lower liquid temperature. This would have facilitated chemical reactions to link heat transfer and harness energy. Another perspective is that lengthy thermography, step 6, gathers energy by facilitating heat transfer from a heat source at its base within the substrate to a sink at the terminus of the colder structure. Ultimately, the free-floating autotroph may have developed the capacity for self-propulsion, transforming into a motile thermotroph, step 7. The solar system's most potent magnetosphere beyond the Sun also offered a significant energy source. The initial organisms to develop the capacity to utilize magnetic energy are undoubtedly transitional, such as a magnetothermograph, step 8, and a magnetochematroph, step 9. These may have subsequently evolved into totally magnetotropic entities. A mobile magnetograph, step 10, harnesses energy using specific cellular mechanisms that segregate charges to create energy-producing gradients. This functions analogously to the thylakoid membranes in plant chloroplasts, which retain electrons dissociated from water through light energy. Reed-shaped magnetotrophs, step 11, would represent a version of this concept. The Lorentz force-induced electrical currents along the length of their elongated bodies would have provided power. Consumers may have adapted to consume each variety with diverse producers currently accessible for sustenance. Ice grazers, step 12, and substrate grazers, step 13, which consume producers residing on ice and substrate, respectively, were likely among the earliest in this classification. Subsequently, creatures capable of buoyancy, step 14, exhibiting high mobility, consuming any available prey, step 15, and exclusively feeding on reeds or plant-like organisms that had developed by that stage, step 16, could have introduced an additional tier to the food chain. In the ever-changing environment that has always existed, life may have flourished in the subterranean lakes of liquid and permeated the ephemeral slurries of the substrate, provided that the temperatures stayed sufficiently warm to avert freezing. Undoubtedly, the freezing would occur, however. In the early stages of life on Io, selection pressure likely facilitated the evolution of cryptic organisms capable of enduring prolonged periods of suspended animation until further lava flows or fresh fissures in the crust introduced heat, prompting their awakening. Consequently, secretive varieties of magnetotrophs, step 17, thermotrophs, step 18, motile consumers, step 19, and vegetative consumers, step 20, have emerged. Detrivores, step 21, would have emerged early in all ecosystems, while cryptic detrivores, step 22, would have developed alongside other cryptobiotic organisms. The duration and size of subterranean lakes of liquid remain uncertain. Whether they exist as pools within lava tube caves or resemble groundwater on Earth, where spatial and habitat fragmentation could facilitate the development of a reasonably complex ecosystem. This complicates the prediction of the ecological type. A multi-layer trophic structure may arise if extensive and durable liquid-filled subterranean layers are present. Figure 9.11 illustrates that 11 producers, 5 consumers, 3 of whom may occupy a secondary or higher trophic level, and 2 detrivores coexisting represent the lowest biodiversity observed on Io. It may be significantly more comprehensive than that. Another concern is that the framework for simplification may overstate biodiversity and ecological complexity if biochemistry or energy extraction is ineffective in that setting. The alternative habitat would be considerably simpler, comprising cryptic species integrated within the substrate that activates only briefly. Like all ecosystems, it would confine its existence to the interstitial voids between grains of sand and soil. A limited number of microbial producers and an even smaller number of microbial consumers would be intrigued by the degree of life at the slushy peripheries of lava fields and geothermal hotspots. The overall biomass of all ecosystems depends on the quantity of biologically usable energy that may be extracted from the environment. Io possesses abundant energy, yet our limited understanding of its effective utilization renders any estimation of biomass and inference of ecological complexity on Io speculative. On Io, life in subterranean pools of liquid SO2 mirrors that of Europa's subsurface ocean, where life is predominantly found in the dark, often inhabiting the floors and ceilings of liquid environments. However, the parallels cease at that point. The solvent is sulfur dioxide, which comprises sulfur dioxide and hydrogen sulfide, and may have a role within cells rather than water. This indicates that the biochemistry and macromolecular structures will significantly diverge from those of water-based systems. The temperature is significantly lower. The energy composition is markedly distinct. However, a pressing necessity for life on Io is entirely lacking on Europa. Life can only thrive inside a limited thermal window, which opens and closes sporadically and unpredictably. Particle emissions from Io's surface engage with Jupiter's formidable magnetosphere in a plasma radiation environment that would be lethal to even the most radiation-resistant creatures on Earth. Consequently, any life form must possess a strong resistance to detrimental radiation to maintain macromolecular integrity. Investigating radiation-resistant creatures on Earth may provide insights for accomplishing this objective. Deinococcus radiodurans is one of the most renowned radiation-resistant microorganisms. Due to natural selection for desiccation resistance, it has developed resilience to elevated amounts of radioactivity and ultraviolet radiation and to cytotoxic chemicals, heat, and extremely high sound velocities. The toroidal configuration of DNA. Radiodurans exhibit an atypically dense and laterally organized structure which may elucidate their resistance to radiation and desiccation. The DNA toroid comprises 4 compartments, each housing a single copy of DNA confined within the structured DNA toroid. Moreover, the DNA is structured in a distinctive ring that inhibits fragmented DNA produced by radiation exposure from dispersing freely inside the cytoplasm. Consequently, unlike other microbes, D. radiodurans can preserve fragmented genetic material by securely encasing the severed DNA segments within a circular structure. The pieces, held close, ultimately reunite in their accurate original sequence, rebuilding the DNA strands. 9. The presence of DNA or similar molecules in potential creatures on Io is uncertain. This comparison examines radiation resistance on Earth with that on Io, where researchers have shown that some cellular components can safeguard against molecular fragmentation, the primary threat posed by Io's elevated radiation levels. Rates will be sluggish as they can only transpire at temperatures well below the freezing point of water. Metabolism is confined to the temperature range of -60 degrees Celsius to -75 degrees Celsius, as both sulfur dioxide and sulfur dioxide 22-sulfur exist as liquids within this interval. H2S has a crucial role in the intracellular processes of Ionian creatures. Narrow thermal activity ranges, in principle, present no issue. Birds and mammals confine their allele metabolism to a limited spectrum. This indicates a widespread anticipation of diminished reaction rates. It exemplifies the archetype of R-selected populations, as defined by ecologists. The notation denotes a mathematical model for opportunistic population expansion, characterized by a limited period for reproduction and elevated mortality rates. Populations exposed to Tor-selective pressure reproduce swiftly and expand fast under favorable conditions. This phenomenon transpires when a surge of warmth activates enigmatic organisms that abruptly liquefy their environment. The unpredictable geological activity on Io may lead to the sudden eruption and vaporization of an entire reservoir, although less indicative of enduring subterranean pools. Consequently, R-selected species function in both habitat types. Reproduction in R-selected populations occurs rapidly. The number of offspring is substantial, and their average size is diminutive. Growth rates are accelerated, a characteristic preferred by natural selection in environments not persistently favorable for growth. These constitute theoretical predictions. The reproductive and growth patterns of actual populations are influenced by various factors, including space, food availability, competition levels, and ecological complexity, all of which remain unknown for potential life on Io. It is plausible to anticipate that most potential life forms are microbial, typified by simple, quick, asexual reproduction. Nevertheless, this assertion cannot be made with certainty. A creature on LO can accept a conservative perspective on energy. This results in a limited number of motile forms, as the low operational temperatures suggest a correspondingly low degree of motility. Most life on Io, similar to subsurface life in other environments excluding deep liquid reservoirs, is more likely to be diminutive and stationary. Sedentary organisms are generally adept at perceiving their immediate environment. Consequently, touch, olfaction, and gustation are significant. The sensory qualities essential for life on Earth are characteristics of individual cells, even unicellular bacteria, suggesting that the most primitive species possess these capacities. The sensory modalities for distance perception, such as vision and auditory cues, are irrelevant for an organism that is neither pursuing objectives nor capable of locomotion. Motile organisms, conversely, inevitably can perceive information on features or things in their surroundings from a distance. Photoreception in the subsurface of LO would be ineffective, but sound or vibration and electromagnetic sense could be significant for the limited mobile life forms anticipated. It may appear presumptuous to propose that certain species on a planetary body, where most scientists question the existence of life, could possess a degree of intellect. The predominant life forms on Io are likely composed of bacteria and fungus, exhibiting little discernible behavior or intelligence. If permanent liquid pools host sufficiently dense and sophisticated ecosystems that include large mobile secondary or tertiary consumers, requiring an integrative apparatus such as a nervous system, they may exhibit a degree of intelligence. The largest brained animals now on Earth, and the most intellectual non-hominids, are marine mammals characterized by poor vision yet exceptional auditory capabilities. Io is the fourth biggest moon in the solar system, possessing a slightly lower density than Mars. However, it resembles a pizza more than a planet due to the diverse array of multicolored sulfur compounds emitted from its incessant volcanic eruptions. It experiences gravitational bending unparalleled in our region of the cosmos as it orbits between the immense gravitational influence of Jupiter and three substantial partners. The remarkable volcanic nature is the predominant characteristic of Io. Fountains of superheated sulfur compounds erupt to altitudes of hundreds of kilometers above the surface, subsequently descending as snow. A surface temperature of -180 degrees Celsius prevents even sulfur dioxide and sulfur dioxide 22 sulfur from hydrogen sulfide from remaining solid, except in areas where internal heat causes them to melt into beneath liquid pools. At any moment, a minimum of 12 volcanic hotspots emit lava that liquefies the surrounding ice layer. This establishes a secondary transient habitat for liquid SO2, MiSO2, to amalgamate with the mineralized crust. These two volatile and transient pools of liquid sulfur dioxide are the most probable environments for life, if it exists, on Io. H2S is more likely to function as a solvent within cells, while larger molecules would likely include more quantities of sulfur, nitrogen, phosphorus, and other components to construct their backbones. It would represent a life form characterized by unique chemistry, regulated by metabolism, and exhibiting structures and functions markedly different from our experiences. It would exist entirely underground and could only flourish within a specific, limited temperature range. However, this might occur, albeit temporarily, in local pools or over short distances of terrain whenever a hot spot emerged or a flow of lava progressed. The existence of Io predominantly exemplifies an edge effect, as is the case universally. The edges are more pronounced and dynamic than anywhere else in the solar system. This emphasizes advantageous biological traits, such as rapid reproduction, swift growth, and the capacity to endure in a concealed state of suspended animation for an extended duration. Life on Io exemplifies the apex of development towards cryptobiotic organisms inside our solar system. It is not a significant priority on anyone's agenda for additional astrobiological research. Nevertheless, it would be erroneous to dismiss it entirely. Scientific reasoning and logic endorse the potential for life in such a context, notwithstanding the unpromising outlook from our terrestrial perspective. If life is discovered there in the future, it will significantly expand our understanding of the nature of life. With the potential exception of the subsequent two worlds we will examine, no location offers as much potential for astonishment and enjoyment as the initial images of this pizza-colored phenomenon experienced by Linda Morabito and the rest of us in spring. Petrolakes. Existence in reservoirs of organic liquids akin to that on Titan. In 1655, Saturn was the most distant planet from Earth in the known solar system, and the rudimentary telescopes of that era unveiled a mystery. Occasionally, the planet appeared to possess handles on both sides, while at other moments, the bulges resembling handles vanished. Christian Huygens, born into an affluent Dutch family of high standing, was permitted by his father to solely pursue his interests in mathematics, mechanics, optics, and astronomy. Utilizing a significantly enhanced telescope compared to its predecessors, he discerned sufficient detail regarding distant planets to hypothesize that the handles were rings surrounding the planet, occasionally observed at an angle towards Earth, and at other times viewed edge-on from Earth, rendering them imperceptible. During consecutive evenings of seeing Saturn's bulges, Huygens saw what he initially perceived as a bright star traveling in front of and then behind the planet, approximately within the same plane as its rings. He accurately inferred that what he observed was the inaugural moon of a planet distinct from Earth and Jupiter. Initially referred to as Luna Satumi, and subsequently dubbed Titan, the moon became the sixth recognized satellite of planets. In the solar system, Dutch astronomer Gerard Kuiper was engaged in radar countermeasures in the United States, following Galileo's discovery of Earth's surface and Jupiter's 4 moons. In the late winter of 1943, during World War II, he opted to take a respite to work at the recently constructed McDonald Observatory in the Davis Mountains of West Texas, near the little hamlet of Marfa, which would later gain notoriety for its sporadic nocturnal lights of enigmatic origin. By chance, one evening, multiple significant satellites in the outer solar system aligned, prompting him to direct his spectroscope at each of them. Unexpectedly, a definitive signal of methane gas emerged in Titan's spectrum, the inaugural indication of an atmosphere on a moon. Subsequently, it was shown that Titan's atmosphere is predominantly composed of nitrogen, rendering Titan the sole celestial planet in the solar system with a nitrogen-rich atmosphere equal to Earth's. The existence of methane, an organic substance potentially indicative of life, intensified interest in Titan and prompted the most complex and costly robotic expedition in the annals of space exploration: the Cassini-Huygens mission to Saturn and Titan. Before the launch of the Cassini-Huygens mission, Titan was encountered by Voyager 1, which captured a detailed photograph during its transit through the Saturnian system in November 1980. Characterizing this highly awaited view of Titan as a disappointment is an understatement. At its nearest proximity, Titan appeared as a uniform orange sphere, shrouded in a dense cloud that concealed its surface. The smog below was presumed to be a hydrocarbon haze of indeterminate composition, as indicated by the blue haze in the upper atmosphere, 10.2 degrees Celsius, which corresponds with the established existence of methane. The atmosphere mostly consists of nitrogen, with fewer methane, ethane, argon, and carbon monoxide, along with minor levels of other hydrocarbons, hydrocyanic acid, and nitrites, organic compounds containing nitrogen. It ascends to an elevation exceeding 100 kilometers, generating an air column that is 1.5 times the mass of Earth's atmosphere. We observe a higher prevalence of the heavy nitrogen isotope, 15N2, than anticipated based on solar abundance predictions. Due to the favored escape of lighter isotopes into space throughout time, Titan's primordial atmosphere was likely denser and more substantial than it is presently at elevated altitudes. Ultraviolet light and ionizing radiation form reactive molecules from methane and nitrogen. These molecules form larger organic compounds, such as benzene and polycyclic aromatic hydrocarbons, PAHs. The method generates substantial ionized organic molecules. Combined with benzene and PAHs, they can produce tholins and intricate hydrocarbon nitrile complexes. 3. These ultimately descend to lower, cooler strata of the atmosphere, where they coalesce into layers of smog-like haze. Ethane and methane generate locally prevalent clouds at altitudes between 30 and 50 kilometers, potentially as a result of methane outgassing from the interior. The surface temperature is around minus 180 degrees Celsius, 292 degrees Fahrenheit. Although water ice constitutes a significant fraction of Titan's mass, at that temperature, ice possesses the hardness of rock and appears accordingly, 10.3 B. Nonetheless, methane and ethane can remain liquid at such temperatures and pressure on the surface. Upon descending to the lower, cooler regions of the sky, they coalesce into droplets of organic liquids and precipitate from the clouds, creating drainage channels and accumulating in basins, 10.4. The polar regions, predictably, have a concentration of ethane lakes due to this more significant effect, 10.5. Time-lapse photographs have demonstrated the migration of clouds over durations spanning from hours to days. Dune formations exhibit indications of locally changing surface breezes. The polar lakes of methane and ethane are more prominent near the poles during winter darkness and less abundant during summer sunlight, reflecting seasonal fluctuations. Consequently, Titan's meteorological conditions encompass wind, precipitation, and seasonal variations. For decades, it has been established that Titan possesses the sole nitrogen-rich atmosphere, apart from Earth, within the solar system. Researchers hypothesized that Titan's surface would be akin to that of Ganymede, a marginally larger icy moon, characterized by a predominantly flat, cratered icy terrain that might contain lakes, seas, or possibly a global ocean of ethane or methane, when Voyager 1 encountered Titan in 1980, and revealed that its density paralleled that of other icy moons, and that its surface temperature was sufficiently low to liquefy hydrocarbons. When radar first penetrated Titan's orange haze, revealing the contours of continental-sized formations, distinct from those observed on other frozen satellites yet resembling Earth's features, public interest in Titan intensified. Titan's surface composition is distinct from Earth's and other icy satellites. The crust of Titan consists of ice and granular organic molecules, in contrast to the silicates found on Earth and the predominantly water-ice composition of Ganymede. However, in its topography, Titan resembles Earth somewhat. The terrain consists of rugged and disjointed land masses encircling low-lying basins filled with liquids at the poles and sand dunes at mid-latitudes, Figure 10.4-6. The landscape has raised topography intersected by dendritic channels resembling converging streams or occasionally broad conduits for substantial liquid volumes that discharge into flatter, low-lying plains, 10.4. Radar imaging of the surface has become increasingly comprehensive, confirming the existence of lakes or seas of liquid hydrocarbons, primarily located near the poles during winter. Recent photographs of Titan's northern pole, captured while it was oriented away from the Sun, reveal a body comparable in size to Lake Superior, situated on the Canada-USA border. Figure 10.5. Big and small basins are present at various latitudes, indicating that liquid bodies may intermittently inundate low-lying regions. Upon the Huygens lander's descent into the basin, the apparatus's thermal energy induced methane sublimation. Hydrocarbons from intermittent flooding may rapidly evaporate, resulting in saturated basins. Certain polar lakes have minimal radar reflectivity, indicating significant depths that may contribute to their longevity. Figure 10.4c. The erosion or failure of surface terrain resulting from the discharge of subterranean liquid reservoirs may have led to the formation of channels across uplands or basins. Consequently, atmospheric precipitation and subterranean liquid displacement may influence Titan's surface morphology. Rifts, discontinuities, and other indicators of geological activity imply that dynamic forces have sculpted Titan's surface. Titan exhibits volcanic characteristics, mostly releasing a slurry of ammonia water from these processes. Impact craters are infrequent on Titan. Only substantial meteorites reach the surface because of the tight atmosphere, and we have detected fewer than 12 impact craters. In contrast, hundreds are present on the surface of Callisto, Jupiter's similarly sized moon. Consequently, Titan's history must be defined by significant weathering and resurfacing. A comprehensive model of Titan's interior can be constructed by integrating many forms of evidence, including data on the planet's density and the composition and history of its atmosphere. Despite the variations in the specifics of competing models, we can generalize them collectively, as depicted in Figure 10.7. During the initial phases of Titan's development, a solid core composed of silicates and/or denser metals segregated from water and other volatiles, including substantial quantities of ammonia and methane. It established itself at the planet's center. Gravitational collapse and radioactive decay persist in generating heat that fuels continuous geological action. The heat flux from the core propels softer ice containing dissolved ammonia and methane to the surface. The volatiles significantly reduce the melting point of water. The emitted heat liquefies the ice at a depth under the surface, forming a worldwide stratum of a highly alkaline solution comprising water, ammonia, and various organic components. Close to the surface, the ammonia-water solution solidifies at temperatures sufficiently low to retain methane in a solid state. Sudden alterations in thermal flow or other variables induce the melting of water, resulting in a cryovolcanic eruption of ammonia water and methane gas. Saturn's biggest moon, Titan, is an unparalleled planetesimal in the solar system. Its atmosphere resembles primordial Earth, characterized by predominant nitrogen and methane gases. Nonetheless, it is significantly smaller and more distant from the Sun than Earth. Its dimensions and density closely approximate those of Ganymede. Nonetheless, it significantly differs from Ganymede in terms of atmospheric and surface attributes. Understanding Titan's uniqueness necessitates reconstructing its history, a formidable job for such a distant and enigmatic entity. The subsequent text presents our distilled interpretation of the research and models proposed by authorities in Titan's planetology 2, 4 to 6. 1. Approximately 4.5 billion years ago, on the remote outskirts of the solar system, the protoplanetary disk destined to form Saturn and its moons commenced its aggregation. The cause of the abnormally high concentration of chemically reduced, hydrogen-bearing molecules remains ambiguous, whether due to the distance from the Sun, the extremely low temperature at that range, or other considerations. Methane, CH4, and ammonia, NH3, were the most prominent. 2. Saturn accumulated the majority of the material in the disk, condensing heavy elements into a metallic core sufficiently massive to retain hydrogen and helium. This resulted in a gas giant planet that Jupiter in our solar system surpassed in size. 3. At a distance of 1.22 million kilometers, about 758,000 miles, almost 90% of the residual material descended to the surface. It transformed into a composite of minerals and ice, sufficiently substantial to retain the volatile methane and ammonia, yet insufficient for the lighter hydrogen. This became Titan, the largest satellite of any planet outside the Jovian system, second in size, somewhat, to Ganymede. 4. The atmosphere composed of methane and ammonia seems substantial, potentially the most voluminous and dense atmosphere of any planetary body, aside from the gas giants, during the primordial epochs of the solar system. Titan's position, comparatively remote from Saturn's gravitational influence, more away than Ganymede is from Jupiter, protected it from the extent of meteorite impacts that seemingly stripped the atmospheres of the similarly sized Ganymede and Callisto. 5. Like other frigid outer satellites, Titan possessed ample water. Nevertheless, at minus 180 degrees Celsius, it was solidly frozen near the surface. However, beneath the crust, it is probable that the heat from the core generates aqueous solutions of ammonia. 6. Simultaneously, ionizing and UV rays from space interacted with atmospheric methane to produce more complex organic compounds. This produced tholins, a form of haze that envelops the entire planet. 10.2. 7. The lower atmosphere was sufficiently frigid that it could not retain methane and ethane in gaseous form, resulting in their precipitation, accompanied by the denser tholins. Ethane reservoirs, potentially of oceanic magnitude, in the past, inundated the surface and persist now in ponds, lakes, and seas next to the poles. 8. The identical radiation transforming methane into a more complex atmospheric mixture of organic compounds likewise dissociated ammonia into its fundamental nitrogen and hydrogen atoms. Titan's insufficient size resulted in the loss of hydrogen to space, leading to an atmosphere predominantly composed of molecular nitrogen, N2, with a heightened 15N, 2 to 14N, 2 ratio. 9. As Titan aged, it depleted a significant portion of its atmosphere, yet intriguingly retained methane. All calculations suggest that methane should have long since disappeared unless it is being replenished. This is also pertinent to Earth's atmosphere, as biogenic sources predominantly contribute to the surprisingly elevated methane levels. While this phenomenon may also occur on Titan, Most methane in Titan's atmosphere originates from its interior venting, supported by substantial evidence of cryovolcanic eruptions. 10. Significant meteorites have impacted Titan, necessitating substantial size to endure the dense atmosphere. The craters formed by these infrequent catastrophes have not endured for long due to weathering and cryovolcanism. Consequently, Titan's surface remains perpetually youthful. In several respects, the conditions for life on Titan are favorable. Titan possesses ample carbon-based precursors for biomolecules, subterranean and surface liquids, and a thick protective atmosphere surrounding the satellite. From the standpoint of known life, the conditions for existence are abysmal. The surface temperature is excessively low for water-based life. The liquids are significantly non-polar, and the potential for a chemical cycle seems constrained. Is it possible for life, as we understand it, to exist in a remote region of the universe? Each press release regarding the recent observations of Titan either commences or concludes with the assertion that scientists consider it a potential analogue for conditions on primordial Earth. The abundant availability of organic compounds is indeed accurate. That is all. Titan's composition, solar distance, orbital properties, dimensions, temperature, and neighboring celestial bodies differ significantly from Earth's, indicating that the histories have likely diverged from the first. If Titan is found to support life, it is more probable that we will discover the diversity of life on other planets, rather than acquire a significant understanding of the origins and evolution of life on Earth. Titan's atmosphere is a rich reservoir of organic molecules. Methane and nitrogen in the upper atmosphere generate various hydrocarbons, nitrites, and polycyclic aromatic hydrocarbons, PAHIGs. The frigid temperatures of Titan's atmosphere ionize several smaller organic molecules, leading to enhanced reaction kinetics. Researchers have identified negatively charged molecules comparable in size to numerous amino acids. To establish the existence of living beings on Titan, we require a minimum of two fundamental components. Initially, there must be the ability to establish boundaries akin to membranes that encase the metabolic systems of terrestrial creatures. We posit that aqueous ammonia solvents constitute the subterranean reservoirs on Titan. In these solvents, lipophilic membranes can function similarly to their behavior in any aqueous solvent. Nevertheless, ethane and methane surface pools are expected to exhibit more complex membrane chemistry. The tholins that fall as solid deposits are insoluble in ethane. They may cross-link to create a sheath or film that exhibits structural stability in hydrophobic liquids. Silicon compounds, such as silane or polysilane, may constitute a component of certain structural barriers, as silanes exhibit stability at extremely low temperatures under reducing circumstances. Considering the wide variety of glass, plastics, and other materials produced on Earth that can contain liquids incompatible with water, the concept of creating semi-permeable boundaries stable in organic solvents is logical. Such possibilities remain hypothetical. Nonetheless, at this juncture, we lack knowledge regarding the surface chemistry on Titan. The secondary requirement for chemical building blocks is the synthesis of informative molecules, specifically big molecules with diverse structures. Titan should streamline this process, as carbon polymers are the optimal substrate for synthesizing macromolecules with substantial information density. A straightforward method for synthesizing a biopolymer utilizing chemicals identified on Titan is illustrated in Figure 10.8. This elongated polymer possesses a carbon-nitrogen backbone dash, N equals C dash C dash N equals C dash C dash, and can be synthesized using hydrocyanic acid and other nitriles. Each alternate carbon atom would possess a distinct chemical group, akin to DNA's 4 diverse nitrogenous bases, Figure 2.7. The arrangement of the variable groups represents information. It is evident how information gets replicated if we postulate the existence of a template mechanism that governs the sequence of side group incorporation. A polymer of this nature may be present on Titan. However, its existence remains uncertain. In a world where gasoline-like materials are plentiful, chemical energy would not present an issue. On Earth, oxidation transforms hydrocarbons such as methane and octane and carbohydrates like glucose and sucrose into water. This process involves utilizing oxygen to cleave the CC and CH bonds, thus storing the energy in alternative molecules. Titan's atmosphere comprises just minimal quantities of free oxygen. Although water represents a substantial potential supply of oxygen on Titan, it is entirely confined within solid ice and consequently is unavailable for chemical reactions. Similarly, carbon dioxide solidifies upon freezing. Increased carbon monoxide levels are present in the atmosphere, and recent studies indicate that the concentrations of carbon dioxide and carbon monoxide may be equilibrated by the gradual influx of oxygen ions from space and maybe water from proximate moons, such as Enceladus. Conversely, other molecules may have harnessed the energy from these processes for biological applications. Nonetheless, the quantity of oxygen accessible for this function is considerably inferior to that necessary for sustaining life on Earth. Another type of energy on Titan may be more logical. The photochemical synthesis of bigger organic compounds in Titan's upper atmosphere produces substantial potential chemical energy. Acetylene, Hc equals Ch, is notably appealing because of the substantial energy contained in its CC triple bond. During the reaction of acetylene with hydrogen to produce methane, the triple bond is cleaved, releasing energy, 9-10. This presents a notably appealing prospect for Titan, as it can transpire in an organic solvent such as methane and ethane. The question remains whether sufficient reactive hydrogen can render this a feasible prospect. We hereby affirm the presence of liquids on Titan's surface. As theorized, they predominantly comprise liquid ethane, undoubtedly containing dissolved methane and various chemical molecules in solution. The exceedingly low temperature indicates that water cannot persist as a liquid on the surface. However, beneath the surface, the temperature escalates to a level at which methane and ethane can no longer exist in a liquid state. But methane is likely retained as a clathrate, or caged molecule, within a water lattice under high pressure. At this elevated temperature, ammonia, which lowers the freezing point of water, is likely present in an aqueous solution, exhibiting a highly basic pH. Titan is extremely frigid. At the surface, a stable temperature of approximately minus 180 degrees Celsius, 290 degrees Fahrenheit below zero, indicates that water is in a solid state. This temperature is marginally over the melting points of methane and ethane, allowing them to exist as liquids on the surface. In the upper atmosphere, adequate solar heat is absorbed to elevate the temperature sufficiently for methane and ethane to evaporate. This allows them to exist as gases until they descend to the cooler regions nearer to the surface and condense as precipitation. The effect of substantial bolides would generate sufficient heat to convert water-ammonia combinations into liquids, potentially creating transient surface pools. An impact crater with a diameter of at least 15 kilometers might retain liquid, ammonia water solutions beneath a frozen crust for hundreds to thousands of years, while rapidly freezing on the surface. Currently, there is no indication of bodies of water on the surface of Titan. Subterranean temperatures ascend towards Titan's core. At significant depths, the temperature surpasses the melting point of aqueous ammonia solutions. Two lines of evidence substantiate the likelihood of significant liquid reservoirs under the surface. The spinning of the surface significantly deviates from Titan's rotational period, indicating the presence of a worldwide subsurface layer of water that separates the mantle from the satellite's interior. Secondly, radar imaging uncovers substantial underground reservoirs of liquid. We posit that cryovolcanic eruptions are induced by heat from radioactive decay and gravity contraction. This is evidence that the Earth's interior is at a higher temperature. Titan's frigid temperatures may inhibit aquatic metabolism as we know it, but they could also moderate the activity of extremely reactive chemical species, such as free radicals. These reactions are essential for a distinct type of energy metabolism that, while impractical on Earth, would function optimally in Titan's temperature and solvent conditions. In the solar system, Titan is the only celestial body of significant size that possesses two distinctly different liquid environments. An aqueous solution containing ammonia and organic molecules below the surface offers a potential environment for aquatic life. This ecosystem may be globally extensive, and thus similar to the subsurface ocean on Europa, albeit with a more alkaline composition. Seasonal variations in availability and scarcity result in the oscillation of ethane-rich ponds, lakes, and seas, which contain larger, more intricate organic compounds above the surface. Intermittent rainfall erodes the surface, replenishing the reservoirs with liquid ethane and methane, figure 10.10. Although the mean precipitation on Titan is perhaps a few centimeters annually, the organic rainfall on Titan is intense, akin to torrential rains in the southwestern United States, potentially exhibiting even greater ferocity. The precipitation is expected to adhere to a pattern determined by air circulation. Consequently, monsoon seasons on Titan resemble those on Earth and are a distinct possibility. Nonetheless, the frequency of monsoons in any one area on Titan remains ambiguous. In locations where liquids flow or persist, they deposit layers of tholins. The Biosphere, derived from lipids of non-polar environments, resembles terrestrial desert habitats, which are often arid although rejuvenated by sporadic rainfall. The precipitation causes the streams to flow and the basins to accumulate liquid, revitalizing them. However, the substance on Titan is ethane and methane instead of water. The two ecosystems likely intersect momentarily due to sporadic geological phenomena like cryovolcanic eruptions. However, they fundamentally remain distinct entities. Titan is captivating from an astrobiological standpoint, as any life present presumably originated on the Moon. The remoteness of Titan from any other celestial planet where life may have existed renders panspermia, the transfer of extraterrestrial life, improbable. Moreover, the potential exists that life may have separately emerged in two distinct environments on Titan. At a minimum, two distinct scenarios must be contemplated regarding the evolution of life since its emergence on Titan, irrespective of its origin and location. During Titan's formative years, when the satellite was presumably enveloped by a vast, if not global ocean, life's emergence and initial evolution likely mirrored the trajectory observed under analogous conditions on Europa. A notable distinction is the increased presence of organic compounds, which may have expedited the emergence of self-organizing systems into living beings more rapidly than in any other location within the solar system. A notable distinction between Titan and Europa is the much reduced intensity of sunlight. On Titan, sunlight is dimmer than 2% of Earth's brightness. Although photosynthesis may occur at low light intensity, we hypothesize that alternative energy sources are more competitive and would have been more plentiful. Therefore, a primordial chemoheterotroph is the most plausible option for the ancestral form of life in Titan's early aquatic environment. Nevertheless, heat and kinetic energy may have also offered other bioenergetic sources. Consequently, thermotrophs and kinetotrophs may have rapidly developed from this primordial species. As discussed in section 10.3.1.2, methanogenesis via acetylene reduction is a compelling concept, suggesting that benthic and lithotrophic methanogens may have been among the earliest life forms on Titan. Organic compounds were readily available in the primordial ocean. Following the establishment of biochemical pathways for processing, Titan's initial organochemotroph would have been a microbe that adapted to utilize this plentiful, high-energy fuel source. This progenitor could have given rise to many descendant forms, including microbial biofilms, initially on the ocean floor and subsequently at the ice ceiling as the ocean froze. Flotation filter feeders, akin to jellyfish on Earth, and various mobile consumers may have also evolved, subsequently supplying nutrients for higher-order flotation and mobile consumers. The progenitors of kinetoscopes may have generated both benthic and ceiling ciliates and benthic reeds that derive energy from water currents. Consumers, such as ceiling scrapers, may have developed to prey on these producers. Microbial detrivores and more complex fungal-like detrivores are equally probable as other eaters. The elevated dissolved ammonia concentration rendered the water alkaline, necessitating adaptation among all living forms in this ecosystem. The initial organochematroph may have specialized in the management of hydrocarbons. This adaptation would have been especially appropriate for the sporadic bodies of water on or near the surface, where hydrocarbons would have been in elevated concentrations. An alkalophilic heterotroph capable of tolerating hydrocarbons may have thrived in large meteorite impacts that created ammonia water craters for extended periods, ranging from hundreds to thousands of years. Upon freezing, the aqueous solution would revert to an enigmatic state, a hydrocarbon environment for the genesis and development of life on Titan. When temperatures sufficiently dropped for ethane and methane to precipitate, Titan's surface had frozen completely, encapsulating any residual liquid from the primordial ocean beneath a dense layer of granular ice and organic matter. Basins developed in the uneven landscape, where ethane accumulated in pools sufficiently large to create seas. 10.5. Two distinct worlds now coexisted on the same planetary body, an underground hydrosphere composed of ammonia water and a surface liposphere dotted with ponds, lakes, and seas of hydrocarbons. 10.9. Life presumably originated in the ancient, now subterranean hydrosphere, maintained in a liquid state by Titan's internal heat and the freezing point drop caused by ammonia and other solutes. Consequently, the inquiry emerges about whether life in the liposphere above may have arisen from an aquatic progenitor rather than independently developing in a distinct hydrocarbon environment on the surface. On the one hand, living in ethane would necessitate such unique characteristics that an independent origin seems highly likely. Titan's transformation from a liquid water environment to a frozen landscape of ethane and methane lakes would not have occurred instantaneously. Tholins collect in the atmosphere before descending to the surface, encapsulating methane in the water during its conversion into ice. Eventually, the substrate transformed into a petroleum-rich sludge, exerting pressure and allowing the organism to adapt to hydrocarbons more effectively. We hypothesize that all life forms in the liposphere descended from a single progenitor, an ancestral hydrophobe. Titan possesses several chemical molecules, indicating that the initial biological systems originated from multiple sources. For simplicity, we presume that they all derived from the same ancestor. Figure 10.11 examines the potential origins of the ancestral hydrophobe through two distinct pathways. Provided that hydrocarbon-based life initiates independently from aquatic life, chemoheterotrophs emerging as self-organizing systems in liquid ethane or methane represent a potential origin of life. Conversely, an ancestor that may have thrived in aquatic environments and hydrocarbons could have adapted effectively to liquid ethane. This resulted in developing the ancestral hydrophobe essential for existence in the liposphere. Nonetheless, the last common ancestor and all ensuing liquid hydrocarbon life exhibited markedly different features from those described. These characteristics encompass 1. A structural boundary that remains stable in a hydrophobic solvent. 2. An internal solvent that remains liquid at temperatures rendering liquid water unfeasible. And 3. the capacity to sustain metabolism at temperatures significantly lower than those previously examined or rigorously modeled. Despite their alien nature, these qualities have established precedents on Earth. Studies have shown that Fusarium alcanophyllum may proliferate and decompose saturated hydrocarbons with limited oxygen and water availability. 12. This organism's membranes are rich in fatty acids and deficient in more hydrophobic lipids, establishing a durable barrier between the intracellular environment and hydrophobic surroundings. Other significant deviations from typical cellular design encompass the lack of internal membranes. Moreover, researchers have identified a significant presence of microbial life in a liquid asphalt lake in Trinidad, which functions as an analog site for investigating life in hydrocarbons. 13. Envisioning a suitable solvent for life at negative 180 degrees Celsius is difficult, although two plausible choices exist as theoretical options. The initial substance combines ammonia and water that remains liquid at negative 98 degrees Celsius on Titan's surface, even lower than pure ammonia's freezing point. Cells elevated by metabolic activities may utilize it as a polar solvent. In this instance, polar solvent-based biochemistry, as we currently comprehend, would not be unfeasible. Methane is a non-polar substance with a melting point of negative 182 degrees Celsius and a boiling point of negative 162 degrees Celsius. The liquid ethane-methane environment roughly mirrors this temperature range. Biochemical processes in such a solvent could occur at temperatures around ambient conditions, although they would be entirely alien to us. The metabolic hurdles are significant, starting with the necessity to digest substantially reduced organic molecules in a less oxidizing environment. Researchers discovered a spontaneous strain of Bacillus cereus in a Chinese oil field that degrades the long hydrocarbon N-hexadecane. 14. A unique array of enzymes on the bacterium's inner membrane has developed to metabolize the atypical carbon source. Numerous anaerobic bacteria may inhabit and decompose petroleum sludge. A prevalent method for utilizing microorganisms to remediate hydrocarbons involves selecting strains that progressively transition from metabolizing conventional carbon sources to hydrocarbon substrates over multiple generations. What people achieve rapidly, in geological terms via artificial selection, should be accessible for natural selection to influence over significantly extended durations. No Earth parallel adequately reflects the true conditions on Titan. Similar to other instances of extremophilic life on Earth, they demonstrate how natural selection can facilitate the emergence of peculiar features in response to atypical selective pressures. Given millions of years to evolve in an increasingly colder and hydrophobic environment, there is no reason that species exceedingly unusual by Earth standards might not emerge, regardless of the initial circumstances. Lithohydrophobes inhabiting niches beneath the substratum would have evolved from ancestral hydrophobes. The Huygens Landers heat may have elicited a release of methane from the substrate, potentially leading to the saturation of Titan's surface with hydrocarbons. If true, microbial hydrophobes residing in the saturated substrate may be prevalent, regardless of their location underneath hydrocarbon pools. If these creatures are methanogens and exist in substantial quantities, the methane they generate may contribute to continuously replenishing atmospheric methane. Ethane biofilms that inhabit the substrates of ponds, lakes, and oceans represent an early counterpart of the liposphere, possibly connected to it. In these hydrophobic biofilms, the organisms may be aggregated or may represent a singular creature that spans a substantial area, akin to the behavior of slime molds that amalgamate their cells to form multicellular entities in certain circumstances. These biofilms would have proliferated across the substrate of hydrocarbon pools, shielded from desiccation by the superjacent liquid. Nevertheless, the subsequent ethane precipitation may have revitalized the cryptobiotic biofilms that endured during the evaporation of the pools. Wherever biofilms could proliferate, biofilm grazers evolved to consume them. They likely existed in those environments. Flotation hydrophobes and encrusted filter feeders are two other descendant types that may have emerged. They would have facilitated the emergence of higher-order consumers, such as a mega-bubble floater capable of preying on lesser inhabitants of the Liposphere. The Huygens lander and Cassini satellite have transmitted images to Earth that depict the channels on Titan's surface as if they are covered with a dark substance like tar. Numerous experts believe this could be a layer of tholins, anticipated on theoretical grounds, to cover a significant portion of Titan's surface. We shall designate it as an ooze of a certain kind. Regardless of its composition, it may contain species unique to that specific makeup. We hypothesize that certain ooze inhabitants occupy this niche. If biofilm grazers have evolved to consume biofilms, they may have led to the emergence of ooze burrowers that excavate the oozing and feed on its inhabitants. The two hypothesized biospheres on Titan would need the presence of two separate ecosystems. The underground hydrosphere is expected to be similar to that of Europa, with the notable exception that Titan's subsurface hydrosphere is likely more alkaline. Like that body, the hydrosphere would be divided into two primary regions, with microbial and stationary producers on the substrate and above the subterranean ammonia water reservoirs. Floating forms may inhabit the intervening volumes at a diminished density as the distance from the producers increases. The Liposphere would appear unlike any known entity on Earth and may be unique inside our solar system, except Triton, Chapter 11. This biosphere comprises two primary components, one located on the substrate of liquid hydrocarbon pools, and the other along the channels where a liquid amalgamation of ethane and methane traverses downward, as a viscous ooze of tholins resembling tar. We hypothesize that the trophic architecture of both principal ecosystems on Titan is superficial, indicating that food chains would be limited in extent. Our rationale is predicated on the premise that 1. The extreme cold impedes mobility, complicating a predatory existence, and 2. The abundance of organic nutrients diminishes the likelihood of consumer activity. The presence of consumers in Figure 10.11 is somewhat conjectural, although being a theoretical possibility. Severe cold is the primary determinant for any life on Titan. The plentiful presence of organic molecules serves as possible energy sources and structural components. If, during the early stages of evolution, a mechanism to harness this substantial chemical energy emerged, the biological characteristics of Titan would rely on the efficacy of metabolic improvements. These would be influenced by Titan's distinctive chemistry and constrained by the capabilities of that chemistry at elevated temperatures. Titan possesses numerous organic substances in its atmosphere, on its surface, within its lakes and seas of petrochemicals, and beneath its surface. Consequently, self-organizing metabolic systems likely emerged early in evolution to utilize the abundant chemical energy. Two factors that may diminish optimism for the rapid stabilization of metabolism in this environment are 1. The scarcity of free chemicals capable of facilitating robust oxidation-reduction cycles, and 2. The inhibitory effect of cold temperatures on reaction rates. The initial issue may hinder our terracentric perspective, which often depends on oxygen-containing chemicals to oxidize organic molecules. Although little oxygen enters Titan's atmosphere, it is present in a very limited supply and is insufficient worldwide for bioenergetics. Many unsaturated carbon bonds, double and triple, are present, providing potential energy sources. Section 10.3.1.2 converts acetylene into methane. Nonetheless, it remains uncertain if sufficient reactive hydrogen exists. Nitrogen may substitute for oxygen in facilitating oxidation reduction cycles on Titan. 15. Indeed, an inexhaustible supply of carbon-bonded hydrogen exists among a vast array of hydrocarbons, contingent upon utilizing thermodynamically advantageous processes to convert them into molecules such as acetylene for energy release. It is essential to acknowledge that evolution is highly innovative. There is no reason to question that a novel metabolic pathway, now unidentified, may have developed under Titan's circumstances to supply the energy necessary for any potential life forms present. Similarly, cold is a comparative phrase. The development of extremophiles on Earth demonstrates that adaptations arise in response to prevailing conditions. All chemical reactions occur at a reduced rate at lower temperatures. Yet, natural selection necessitates reactions occurring swiftly at the requisite temperature to fulfill their essential functions. Metabolic rates will adapt as rapidly as necessary. From our viewpoint, metabolic rates on Titan are likely to be sluggish. But we must use caution due to our ignorance regarding the nature of those metabolic transformations. Leveraging ample resources and energy in a frigid environment, we foresee gradual development and uncomplicated reproduction. In heterogeneous and stable settings on Earth, reproduction rates are diminished and growth is sluggish. Evolution has generally optimized adaptations for success in stable conditions, reducing death rates. Consequently, organisms can preserve energy by reducing their progeny count, allowing them to grow slowly towards typically greater terminal sizes. Evidence indicates that Titan's weather frequently fluctuates, and considerable habitat fragmentation exists. Nonetheless, the subterranean hydrosphere and the subaqueous or ooze-embedded liposphere are expected to remain stable for an extended duration. The overarching principle of diminished growth and reproduction rates should apply to Titan. It would be impractical to anticipate sexual reproduction. Locating partners and exchanging genetic material requires energy and has some risks. Thus, biologists typically assert that the benefits of genetic recombination must significantly outweigh these drawbacks. Many individuals believe that the advantages arise from establishing a constantly evolving genetic repertoire, enabling the organism to adapt to new obstacles and evade parasites or illness. Reproductive simplicity is probable if no new challenges arise for an extended period, and abundant nutrients facilitate chemoautotrophy as a viable lifestyle for all. This may signify growth by expansion or asexual reproduction. Conversely, if parasitism is prevalent in Titanian life, it may facilitate the evolution of sexual reproduction. We previously noted the potential for recurrent monsoonal precipitation that generates rivers, streams, and lakes in seasonal cycles, similar to creatures on Earth, whose life cycles are intricately linked to substantial seasonal fluctuations in their environment. Hypothetical life on Titan may also be associated with seasonal variations. For example, especially in the desert sands of Titan's mid-latitudes, species may remain dormant until the ethane-methane monsoon season, akin to how plants in the southwestern United States anticipate rare rainfall to flourish. Other species residing in or near the ethane-methane lakes closer to the poles may similarly await the monsoon to precipitate organic nutrients from the atmosphere and down the slopes. The absence of reliable data regarding seasonal variations on Titan complicates even well-informed conjecture. Nonetheless, if life on Titan has adapted to flourish in organic hydrocarbons, it would be peculiar if their life cycle were not intrinsically linked to the seasonal precipitation and rise in organic molecules. If the pursuit of mates is superfluous and organic nutrients are ubiquitous, what is the purpose of movement? This is the probable rationale by which natural selection on Titan would lack a foundation for promoting the evolution of motile life forms. They may exist at one or more consumer levels but are likely to be few and sluggish, consistent with the somewhat flat ecosystem structure referenced in section 10.5 above. Titan's environment likely resembles a moss-laden forest floor, inhabited by a limited number of animal-like entities. On Earth, sensory systems evolved as navigational instruments for locomotion, providing organisms with spatial awareness, discerning between allies and adversaries, and facilitating the requisite muscular actions for suitable conduct. If the creature is stationary, its requirement for sensory information is negligible. Nonetheless, a nutrient-rich chemical milieu would facilitate the advancement of olfaction. Touch sensitivity is crucial, as the social interactions of microorganisms, especially biofilms, rely on mutual recognition or antagonism. The absence of illumination in Titan's environments would render vision insignificant. Sound detection is crucial for predator-prey interactions, and is likely unnecessary in environments with few predators. Touch and olfaction are primordial sensory functions that originated in the earliest microorganisms, which lacked specialized brain structures. The advanced senses of vision and hearing necessitate nerve cells. Nevertheless, the necessity for a neurological system is not apparent in their absence. Cognition, an emergent feature of neural systems, suggests that thinking is improbable in animals devoid of such systems. The metaphor for life on Titan is the grass-covered expanse or the algae-laden pond. The biomass may be substantial, yet it lacks intelligence. Titan is a highly appealing candidate for anybody seeking unique living forms on another celestial body. It integrates familiar life-sustaining elements, such as carbon-based chemistry, with extraterrestrial characteristics including organic compound liquids and extremely low temperatures. An examination by the National Academy of Sciences determined that if life is an intrinsic property of chemical reactivity, it should exist on Titan. The allure of allowing our minds to wander is strong. Consequently, we must use caution in our pursuit of desired findings. By the essence of this book, we have thoroughly explored the spectrum of possibilities for life on Titan. We have proposed only that which is scientifically feasible within the constraints of our current knowledge. However, that knowledge is significantly constrained, and the potential outcomes are highly conjectural. We do not apologize for reasonable speculation. Nonetheless, this call to impartiality necessitates a matching cautionary comment. Titan's environment differs significantly from the known habitats for life on Earth. Our understanding of the generic boundaries of life is insufficient to ascertain whether it can exist under the extraordinary conditions present on Titan. We posit that life may exist under conditions beyond our comprehension. However, we may be mistaken. If life is contingent upon the presence of liquid water, it cannot exist near the surface of Titan or in that intriguing realm. Since its discovery over 350 years ago, Titan has been a uniquely intriguing satellite in our solar system. At its discovery, the sixth known moon of any planet was historically regarded as the largest and is the furthest distant, huge moon from its parent planet. The revelation of Titan's nitrogen and organic-laden atmosphere enhanced its appeal. Nevertheless, that atmosphere maintained its enigma until the Cassini orbiter and Huygens lander penetrated its dense organic haze, unveiling a surface with unexpectedly terrestrial characteristics. Rugged elevations intersected by dendritic channels flowing into basins indicate a land exposed to cycles of precipitation and erosion. Cryovolcanic eruptions and tectonic-like formations indicate persistent geological activity. Rare and substantial impact craters suggest infrequent impacts, intense erosional processes, or a combination of both. The recent identification of significant ethane reservoirs in Titan's poles validates theoretical predictions that the moon's chilly temperature of -180 degrees Celsius is sufficient for ethane and certain methane to precipitate from the atmosphere and persist on the surface for prolonged durations. Titan's atmosphere originates from a significantly larger primordial envelope of ammonia gases. Photolytic degradation transformed ammonia into nitrogen and expelled hydrogen into space, resulting in the annihilation of methane. This resulted in a substantial accumulation of hydrocarbon molecules and ions, transforming the atmosphere into a cauldron of organic substances. Certain substances generated tholins, and layers of them ascended to the surface. Remarkably, the concentration of methane remained constant. This may signify the ongoing methane emission from a substantial subterranean reservoir or the natural generation of methanogens. The potential for life on Titan exists in two separate environments. Substantial evidence suggests the existence of extensive subsurface reserves of liquids, potentially on a global scale, primarily consisting of water-based ammonia solutions. This hydrosphere may match the hypothesized biosphere within Europa's subsurface ocean, supporting a comprehensive aquatic ecology. The liquid ethane pools on the surface and the tar-like tholin layers at the bottoms of channels and potential basins containing liquid hydrocarbons may each offer a unique home. This liposphere would need to support a distinct biosphere of species that develop to thrive in organic solvents at temperatures well below the potential for liquid water. Theoretically, if life existed on Titan, its biomass may be substantial, but its trophic structure would be simplistic. Its many forms are predominantly sedentary, and its metabolism is unprecedented in our experience. The pursuit of life on Titan holds significant relevance as it would enhance our comprehension of life overall if discovered. However, scientific prudence necessitates acknowledging the possibility that it may be entirely absent.